Hi there, Ancient Earth Documentary here. Welcome back to our podcast. Picture this. You're standing on the coastline of what is now Kansas, watching waves crash against sandy beaches. Except Kansas is landlocked, sitting smack in the middle of North America, hundreds of miles from the nearest ocean. But 100 million years ago, you could have built a sandcastle there, gone surfing, maybe even spotted a massive marine reptile gliding through the crystal clear waters. Because Kansas wasn't just near an ocean, it was under one. Welcome to a world where sea levels weren't just a few feet higher than today, but hundreds of meters higher. We're talking about prehistoric Earth, where the geography you know was completely unrecognizable, where entire continents were submerged under vast, shallow seas, where land covered only 18% of the planet's surface compared to 28% today, and where the mechanisms driving these incredible sea level heights were so fundamentally different from anything we see in the modern world that they challenge everything you think you know about our planet's water cycle. Today, we worry about sea level rise, measured in centimeters per decade. But during certain periods of Earth's deep past, the oceans stood 250 meters higher than they do right now. That's not a typo. 250 meters. To put that in perspective, if you took the Statue of Liberty and stacked it on top of itself, the water would still be lapping at Lady Liberty's torch. And this wasn't some brief geological hiccup. These extreme sea levels persisted for millions of years at a time, reshaping continents and creating marine highways where mountain ranges stand today. But here's where it gets really interesting. Even if we melted every single ice sheet on Earth today, every glacier in Greenland, every chunk of ice in Antarctica, sea levels would only rise about 70 meters. That's barely a third of what we see in the geological record. So what was driving these incredible prehistoric sea levels? How did Earth's oceans get so impossibly high? And what does this tell us about our planet's climate system when it operates in full greenhouse mode? The answers lie buried in rock formations that span continents, in the chemistry of ancient marine sediments, and in the fossilized remains of creatures that once swam where cornfields now grow. These geological archives tell the story of a planet that operated by completely different rules, where volcanic forces reshaped entire ocean basins, and where the absence of polar ice caps was just the beginning of a much more complex story. To understand prehistoric sea levels, we need to travel back to one of the most extraordinary periods in Earth's history, the Cretaceous period. This wasn't just the age of dinosaurs stomping around on land. This was the age of marine reptiles, the size of school buses, cruising through inland seas that stretched from the Gulf of Mexico to the Arctic Ocean. Seas that existed because the planet's water budget looked nothing like it does today. During the mid-Cretaceous, roughly 100 million years ago, sea levels reached their absolute peak. We're talking about heights that sound almost fictional. Scientific estimates place Cretaceous sea levels at 170 to 250 meters above present-day levels. The highest point occurred during a time period called the Early Turonian, when the oceans peaked at approximately 240 to 250 meters above where they sit today. Think about your hometown for a moment. Unless you live more than 200 meters above sea level, your entire community would have been underwater during the Cretaceous. Cities like Chicago, sitting at 180 meters above sea level, would have been completely submerged. Even Denver, the mile-high city, would have had water lapping at its suburbs. These weren't temporary floods or storm surges. This was the new normal for millions of years. The Cretaceous world was a water world in the truest sense, with marine environments extending deep into the hearts of continents. North America was split by a massive seaway called the Western Interior Seaway, stretching from the Gulf of Mexico all the way to the Arctic Ocean. This wasn't a river or a lake. This was a full marine environment, complete with sharks, marine reptiles, and creatures that would make today's ocean predators look like minnows. But North America wasn't unique. Similar marine incursions flooded huge portions of South America, Europe, Russia, Africa, and Australia. The familiar continental shapes we see on modern maps simply didn't exist. Instead, the world looked like an archipelago of large islands separated by vast, shallow seas. Now, here's where most people assume they know the answer. Obviously, the planet was warmer, so the ice melted and sea levels rose, right? Well, that's partially correct, but it's barely scratching the surface of what was really happening. The Cretaceous world was indeed warmer, much warmer. But even accounting for the complete absence of polar ice caps, we can only explain about 70 meters of sea level rise. That leaves us with a massive gap of 150 to 180 meters that ice melting simply cannot explain. So what was driving these incredible heights? The answer lies in processes that operate on scales almost too large to comprehend, processes that were reshaping the very structure of Earth's ocean basins while simultaneously pumping enormous volumes of heat and gas into the atmosphere. We're talking about volcanic activity so intense that it makes modern eruptions look like birthday candles. During the Cretaceous, Earth's volcanic systems were operating in overdrive. This wasn't just your typical volcanic activity. This was planetary-scale volcanism that created geological features so massive they permanently altered the shape of ocean basins. The evidence for this volcanic intensity is written in the rock record, with thick deposits of volcanic ash found in Cretaceous marine sediments across the globe. But the real game changers were formations called large igneous provinces, or LIPS. These represent some of the most massive volcanic events in Earth's history, creating enormous underwater plateaus that displaced staggering volumes of seawater. Think of it like dropping a massive rock into a bathtub. The water has to go somewhere, and in Earth's case, it went up. The most spectacular example of this process is the Ontong Java Plateau in the Western Pacific. This single volcanic formation covers an area as large as Alaska and reaches up to 30 kilometers thick. During its formation, it spewed out 100 million cubic kilometers of lava over several million years. To put that in perspective, that's enough volcanic material to bury the entire continental United States under a layer of rock 3 kilometers thick. But the Ontong Java Plateau wasn't alone. The Cretaceous period saw the formation of multiple massive oceanic plateaus, each displacing enormous volumes of seawater. The Kerguelen Plateau in the Indian Ocean, the Manihiki Plateau in the Pacific, and numerous other volcanic constructions all contributed to what scientists call oceanic displacement. These weren't gradual processes building up over tens of millions of years. These were geologically rapid events that could raise global sea levels by tens of meters in just a few million years. The sheer scale of these volcanic episodes is difficult to comprehend. Scientists estimate that increased ocean ridge activity alone could have caused sea levels to rise by 50 to 100 meters above current levels. When you add in the displacement effects of massive oceanic plateaus, you start to understand how the Cretaceous oceans reached such extraordinary heights. But volcanism wasn't just displacing water, it was also fundamentally altering the planet's climate system in ways that amplified sea level rise even further. These massive volcanic events were pumping enormous quantities of carbon dioxide into the atmosphere, creating greenhouse conditions that make our current climate concerns look modest by comparison. During peak volcanic episodes, atmospheric carbon dioxide levels soared well above 1,000 parts per million. For context, pre-industrial atmospheric CO2 was around 280 parts per million, and we're currently approaching 420 parts per million. The Cretaceous atmosphere contained more than twice as much CO2 as our current levels, creating a runaway greenhouse effect that pushed global temperatures far beyond anything in human experience. The results were dramatic. Average global temperatures during the Cretaceous were approximately 6 to 8 degrees Celsius warmer than today. But the polar regions experienced even more extreme warming, with Arctic temperatures reaching over 23 degrees Celsius. These weren't brief heat waves. These were sustained temperature conditions that persisted for millions of years, creating a world where palm trees grew in Alaska and crocodiles basked on Arctic beaches. This extreme warming had a direct impact on sea levels through a process called thermal expansion. As ocean water heats up, it expands, taking up more volume and raising sea levels even without adding any additional water to the system. In today's oceans, thermal expansion accounts for a significant portion of ongoing sea level rise. But during the Cretaceous, with ocean temperatures dramatically higher than today, thermal expansion effects were amplified far beyond anything we observe in the modern world. Scientists estimate that thermal expansion of seawater during the Cretaceous could have contributed tens of meters to global sea level rise. When you're dealing with ocean temperatures that were 10 to 15 degrees warmer than today, the expansion effects become enormous. Deep ocean waters, which today hover around 2 degrees Celsius, reach temperatures of over 13 degrees Celsius during Cretaceous warm periods. This warming extended throughout the entire water column, maximizing the thermal expansion effect. But we're still not done with the mechanisms driving these incredible sea levels. There's another factor that operates on a completely different timescale, but has equally dramatic effects. It has to do with the age and temperature of the ocean floor itself. Here's something most people don't realize about Earth's oceanic crust. It's not all the same age or temperature. New oceanic crust forms at mid-ocean ridges, where volcanic activity creates fresh, hot rock that gradually spreads away from the ridge and cools over millions of years. Young, hot oceanic crust is less dense and takes up more volume than older, cooler, contracted crust. This means that when the average age of oceanic crust is younger, the ocean basins are effectively shallower, forcing sea levels higher. During the Cretaceous, global volcanic activity was so intense that the average age of oceanic crust was much younger than it is today. Mid-ocean ridges were spreading at rates far exceeding modern activity, constantly creating new, hot, expanded crust. Scientists estimate that this ridge thermal expansion effect could have raised Cretaceous sea levels by an additional 150 meters compared to periods when oceanic crust was older and more contracted. This combination of factors creates a perfect storm for extreme sea level elevation. You've got massive volcanic plateaus displacing oceanic water, intense greenhouse warming causing thermal expansion, complete absence of polar ice caps, and younger oceanic crust creating shallower ocean basins. Each mechanism alone could raise sea levels by tens of meters. Combined, they created the most extreme marine conditions in Earth's history. But the Cretaceous wasn't the only period when Earth's oceans reached extraordinary heights. Travel back even further in time to the Eocene epoch, roughly 50 million years ago, and you encounter another world of impossible seas. The Eocene represents what scientists call a greenhouse world on steroids, where global temperatures soared even higher than during the Cretaceous. During the early Eocene climatic optimum, Earth experienced the warmest sustained temperatures of the entire Cenozoic era. We're talking about a planet that was more than 5 degrees Celsius warmer than today, with virtually no ice anywhere on the surface. The polar regions, which today are locked under kilometers of ice, were covered in lush forests where palm trees and alligators thrived in balmy subtropical conditions. Eocene sea levels reached heights of 100 to 150 meters above present levels. While not quite as extreme as the Cretaceous peaks, these elevations still represent a world where massive portions of every continent lay beneath warm, shallow seas. The familiar geography of continents was transformed into chains of tropical islands separated by crystal-clear marine environments. What makes the Eocene particularly fascinating is the speed at which these changes occurred. Unlike the gradual build-up of Cretaceous conditions, The Eocene happened relatively quickly in geological terms. The Paleocene-Eocene thermal maximum, a brief but intense warming event at the beginning of the Eocene, saw global temperatures spike by 5 to 9 degrees Celsius in just a few 100,000 years. This rapid warming was triggered by massive injections of carbon into the atmosphere and oceans, possibly from volcanic activity or the sudden release of methane hydrates from ocean sediments. The result was a climate system that spiraled into extreme greenhouse conditions, with atmospheric carbon dioxide levels exceeding 1,000 parts per million. The thermal expansion effects during the Eocene were even more pronounced than during the Cretaceous. Deep ocean waters, which today barely exceed freezing, warmed to over 13 degrees Celsius. Surface waters in some regions reached temperatures approaching 45 degrees Celsius, creating ocean conditions more like a hot bath than the marine environments we know today. These extreme temperatures had cascading effects throughout the climate system. The enhanced thermal expansion of seawater contributed several meters to global sea level rise beyond what ice melting alone could achieve. When you combine this with the complete absence of polar ice sheets and continued volcanic activity, you get the recipe for another period of extraordinary marine inundation. But Eocene sea levels tell us something crucial about Earth's climate sensitivity. They demonstrate that our planet's climate system has multiple stable states, and that the transition between these states can happen much faster than we might expect. The Eocene world wasn't gradually warming over tens of millions of years. It was a climate system that had flipped into an entirely different mode of operation. Journey even further back in time, to the Paleozoic era, and you encounter sea levels that challenge everything we think we know about Earth's water budget. During the Ordovician period, roughly 450 million years ago, the oceans reached heights that rivaled even the Cretaceous extremes. The Ordovicians saw the highest sea levels of the entire Paleozoic era, with marine waters reaching 200 meters above today's levels. This was a world where the continents were configured completely differently, clustered near the equator with vast polar oceans surrounding them. The low relief of these ancient continents meant that even modest sea level rises could flood enormous areas. What makes Ordovician sea levels particularly remarkable is that they occurred during a period of intense biological innovation. This was when complex marine ecosystems first began to flourish, with the first coral reefs, the first fish, and an explosion of invertebrate diversity. These early marine communities were living in ocean conditions that were far more extreme than anything modern marine life has ever experienced. Ordovician ocean temperatures were scorching by modern standards, with surface waters possibly reaching 45 degrees Celsius in some regions. These hothouse conditions were driven by atmospheric carbon dioxide levels that were many times higher than today, creating greenhouse effects that sustained tropical conditions even in polar regions. The combination of extreme temperatures and high sea levels created vast shallow marine platforms across the continents. These weren't deep ocean basins like we see today, but extensive shallow seas that provided ideal conditions for the evolution of early marine ecosystems. Limestone formations from the Ordovician period, found hundreds of kilometers inland from modern coastlines, preserve the remains of these ancient marine communities. But perhaps the most mind-bending aspect of Ordovician sea levels is how they interacted with the early evolution of life on land. During this period, life was just beginning to colonize terrestrial environments. The first primitive plants were establishing footholds on land, while vast shallow seas dominated the landscape. The geography of this early terrestrial colonization was shaped entirely by these extraordinary marine conditions. The mechanisms driving Ordovician sea levels were similar to those of later periods, but operating in a world with fundamentally different continental configurations. Intense volcanic activity, high atmospheric carbon dioxide levels, complete absence of polar ice, and thermal expansion of superheated seawater all contributed to creating ocean heights that transformed the planet's geography. These Paleozoic sea levels also reveal something important about the long-term stability of Earth's climate system. The transition from the extreme greenhouse conditions of the Ordovician to the icehouse conditions that would eventually develop required massive changes in atmospheric composition, continental positioning, and volcanic activity. These weren't minor adjustments to the climate system. They were fundamental reorganizations of how the planet's energy budget operated. Understanding these ancient sea level extremes requires us to think about Earth's climate system in entirely different terms. We're not just talking about warmer or cooler conditions. We're talking about a planet that operated according to completely different physical principles, where the familiar ice caps, ocean currents, and seasonal patterns that define our modern world simply didn't exist. The geological evidence for these extreme sea levels is preserved in rock formations that span entire continents. Limestone deposits formed in shallow marine environments can be found hundreds of kilometers from modern coastlines, at elevations that would be impossible under current sea level conditions. These aren't isolated deposits. They're continuous formations that extend across vast areas, providing undeniable evidence that marine conditions once dominated regions that are now deep within continental interiors. Marine fossils tell the same story. Remains of ancient sea creatures, from microscopic plankton to massive marine reptiles, are found embedded in rocks that formed on ancient seafloors, now located hundreds of meters above sea level and thousands of kilometers from the nearest ocean. These fossils provide detailed snapshots of marine ecosystems that thrived under environmental conditions far more extreme than anything in the modern world. Chemical signatures preserved in these ancient marine sediments reveal ocean temperatures, atmospheric compositions, and volcanic activity levels that paint a picture of a planet operating in full greenhouse mode. Oxygen isotope ratios in fossil shells indicate ocean temperatures that would be lethal to most modern marine life. Carbon isotope signatures reveal atmospheric carbon dioxide levels that sustained greenhouse effects far beyond our current climate projections. But perhaps the most remarkable aspect of these prehistoric sea level extremes is their duration. These weren't brief episodes or temporary anomalies. The Cretaceous high sea level conditions persisted for roughly 40 million years. The Eocene greenhouse world lasted approximately 20 million years. The Ordovician marine dominance continued for tens of millions of years. These timescales are almost incomprehensible from a human perspective. 40 million years ago, the earliest ancestors of modern mammals were just beginning to diversify. 20 million years encompasses the entire evolutionary history of many modern animal groups. These extreme sea level conditions weren't geological hiccups. They were the dominant state of Earth's climate system for vast stretches of planetary history. The implications of these prehistoric sea levels extend far beyond academic curiosity. They reveal the true range of Earth's climate sensitivity and demonstrate that our planet's climate system can operate in modes that are completely outside the range of human experience. They show us that the familiar ice caps, moderate temperatures, and stable sea levels of the past few million years represent just one possible configuration of Earth's climate system. These ancient climate states also provide crucial insights into how quickly the climate system can transition between different modes of operation. The Paleocene-Eocene thermal maximum demonstrates that massive climate reorganizations can occur in just a few 100,000 years. The end Cretaceous transition shows how rapidly extreme greenhouse conditions can collapse when the underlying volcanic and atmospheric drivers change. What's particularly striking about these prehistoric sea level extremes is how they completely rewrote the rules of ocean circulation and marine chemistry. Today's oceans operate like a massive conveyor belt, with cold water sinking at the poles and warm water rising near the equator, creating the deep ocean currents that distribute heat and nutrients around the globe. But during periods of extreme high sea levels, this entire system broke down. When there are no polar ice caps and ocean temperatures are uniform from equator to pole, the temperature differences that drive modern ocean circulation simply don't exist. Instead of the vigorous mixing we see today, prehistoric oceans often became stratified, with warm surface waters sitting on top of deeper layers that received little oxygen or circulation. This created what scientists call oceanic anoxic events, periods when vast portions of the ocean became essentially lifeless due to lack of oxygen. The evidence for these oxygen-starved oceans is preserved in black shale formations that stretch across multiple continents. These dark, organic-rich rocks formed when massive amounts of dead marine organisms accumulated on seafloors that lacked the oxygen needed for normal decomposition. Ironically, many of the world's largest oil reserves formed during these periods of oceanic stagnation, when organic matter was buried and preserved rather than being recycled by marine ecosystems. The Mancos Shale of Western North America represents one of the most spectacular examples of these anoxic deposits. This formation extends from New Mexico to Montana, preserving evidence of oceanic conditions that persisted for millions of years during the Cretaceous. Similar formations can be found across Europe, Africa, and Asia, demonstrating that oceanic anoxia was a global phenomenon during periods of extreme sea level elevation. But these stagnant ocean conditions weren't just a side effect of high sea levels. They were part of a feedback loop that amplified the very processes driving sea level rise. When ocean circulation slows down, the deep ocean retains heat more effectively, enhancing thermal expansion. When organic matter accumulates on seafloors instead of being decomposed, it removes carbon from the atmosphere temporarily, but also creates conditions for massive methane releases that can trigger additional warming episodes. The chemistry of these prehistoric oceans was unlike anything in the modern world. Surface waters reached temperatures that would instantly kill most modern marine organisms. Acidity levels fluctuated wildly as massive volcanic emissions pumped sulfur compounds into the atmosphere, creating acid rain on a global scale. The ocean floor became a graveyard of accumulated organic matter, creating vast deposits of hydrocarbons that we're still extracting millions of years later. These chemical extremes had profound effects on marine life. During the Cretaceous, the oceans were dominated by species that could tolerate conditions that would be toxic to modern organisms. Massive marine reptiles like Mosasaurus and plesiosaurs thrived in waters that were simultaneously superheated and chemically hostile. These weren't just larger versions of modern marine animals. They were creatures adapted to ocean conditions that no longer exist on Earth. The fossil record from these periods reveals marine ecosystems that operated by completely different rules. Instead of the complex food webs we see in modern oceans, prehistoric marine communities were often dominated by a few highly specialized species that could tolerate extreme conditions. Massive blooms of single-celled organisms created layers of limestone hundreds of meters thick, preserving evidence of oceanic productivity that dwarfed anything in the modern world. Microscopic marine organisms called coccolithophores flourished in these superheated seas, creating the extensive chalk deposits that give the Cretaceous period its name. The White Cliffs of Dover, the limestone formations of Kansas, and similar deposits around the world all formed from the accumulated remains of these tiny organisms. The scale of these deposits is staggering, representing biological productivity that sustained itself for millions of years under conditions that would collapse modern marine ecosystems. These prehistoric marine communities also reveal something crucial about the relationship between temperature and marine productivity. Modern marine ecosystems are most productive in cooler waters where nutrients can circulate effectively. But during periods of extreme greenhouse warming, marine productivity shifted to completely different mechanisms. Instead of nutrient-driven ecosystems, prehistoric oceans were often dominated by organisms that could harvest energy directly from chemical processes or tolerate extreme temperature conditions. The transition between these extreme oceanic states and more familiar conditions reveals the dramatic instability of Earth's climate system when operating in full greenhouse mode. The end of the Cretaceous greenhouse wasn't a gradual cooling. It was a relatively rapid collapse that fundamentally reorganized global climate patterns. The massive volcanic activity that had sustained extreme sea levels for 40 million years began to wane. Atmospheric carbon dioxide levels dropped, and the climate system flipped into a completely different mode of operation. This transition wasn't smooth or predictable. Instead, it was marked by wild fluctuations in temperature, sea level, and oceanic chemistry. The geological record preserves evidence of rapid sea level changes, sudden temperature swings, and massive extinction events as marine ecosystems collapsed and reformed under changing conditions. The familiar stability of modern climate patterns emerged only after millions of years of chaotic transitions. Understanding these prehistoric oceanic conditions also requires us to reconsider our assumptions about the relationship between life and environment. Modern marine ecosystems exist within a relatively narrow range of temperature, chemistry, and circulation conditions, but the prehistoric record shows that life can adapt to oceanic conditions far more extreme than anything in the modern world. This doesn't mean that such conditions are desirable or stable, but it does reveal the remarkable plasticity of marine ecosystems when given enough time to adapt. The implications of these prehistoric oceanic extremes extend beyond understanding ancient climate. They provide crucial insights into how modern marine ecosystems might respond to rapid environmental change. The collapse of oceanic circulation patterns, the development of anoxic conditions, and the dominance of single-celled organisms over complex marine communities all represent potential futures for our current oceans if greenhouse conditions continue to intensify. But these ancient oceanic states also reveal something hopeful about the resilience of Earth's climate system. Despite experiencing conditions far more extreme than current climate projections, the planet eventually transitioned back to more moderate states. Ocean circulation patterns re-established themselves, complex marine ecosystems recovered, and the climate system found new points of stability. This doesn't minimize the challenges of current climate change, but it does demonstrate the long-term adaptability of Earth's environmental systems. The study of prehistoric sea levels also reveals the crucial role of tectonic processes in shaping long-term climate patterns. The extreme sea levels of the Cretaceous and Eocene weren't just the result of atmospheric changes. They were intimately connected to the configuration of continents, the intensity of volcanic activity, and the structure of ocean basins. As continental positions shifted and volcanic activity waned, the underlying drivers of extreme sea levels gradually disappeared. The transition from the scattered continental configurations of the Mesozoic to the more familiar arrangements of the Cenozoic fundamentally altered ocean circulation patterns. As continents drifted into positions that allowed the development of circumpolar currents around Antarctica, the stage was set for the eventual formation of polar ice caps. This wasn't a sudden change, but a gradual process that played out over tens of millions of years. The development of the Antarctic circumpolar current around 34 million years ago marked a crucial turning point in Earth's climate history. For the first time in hundreds of millions of years, ocean circulation patterns developed that could effectively isolate polar regions and allow the accumulation of ice. This represented a fundamental shift from the greenhouse conditions that had dominated earlier periods to the icehouse conditions that would characterize the later Cenozoic. But even after the establishment of Antarctic ice sheets, sea levels remained dramatically higher than modern conditions for millions of years. During the Miocene period, roughly 15 million years ago, global temperatures were only 3 to 4 degrees warmer than today, yet sea levels stood 20 to 40 meters above current positions. This demonstrates that even relatively modest warming can trigger significant ice sheet collapse and substantial sea level rise. The transition to modern icehouse conditions was neither smooth nor permanent. Throughout the Cenozoic, Earth's climate system oscillated between warmer periods with higher sea levels and cooler periods with expanded ice coverage. The Pliocene warm period, just 3 to 4 million years ago, saw atmospheric carbon dioxide levels similar to today's, yet sea levels were 22 meters higher than current positions. This required significant melting of both Greenland and Antarctic ice sheets, providing a sobering preview of potential future sea level rise under continued greenhouse gas emissions. These Cenozoic sea level fluctuations also reveal the complex relationship between atmospheric composition, ice sheet dynamics, and oceanic thermal expansion. Unlike the extreme greenhouse periods of the Mesozoic, Cenozoic sea level changes were primarily driven by the growth and decay of ice sheets, but thermal expansion remained an important component, particularly during rapid warming episodes when ocean temperatures could change faster than ice sheets could respond. The development of sophisticated ice sheet models has allowed scientists to reconstruct the detailed mechanics of these Cenozoic sea level changes. During warm periods, ice sheets didn't simply melt uniformly. Instead, they experienced complex patterns of retreat and collapse, with some regions melting rapidly while others remained stable for millions of years. These patterns were controlled by factors like bedrock topography, ocean circulation, and atmospheric circulation patterns that are only beginning to be understood. The most recent glacial cycles of the past few million years represent just the latest chapter in this long story of sea level change. Even during these relatively recent ice ages, sea levels fluctuated by more than 100 meters as ice sheets advanced and retreated across northern continents. The last glacial maximum, just 20,000 years ago, saw sea levels drop to 130 meters below present levels, exposing vast continental shelves and creating land bridges between continents. But these glacial sea level changes pale in comparison to the extremes of earlier geological periods. The difference between glacial and interglacial sea levels represents just a fraction of the range documented in Earth's deep past. The prehistoric sea level extremes we've explored reveal that our planet's climate system is capable of operating in modes that are completely outside the range of human experience or even recent geological history. The study of these prehistoric extremes also highlights the importance of understanding climate system sensitivity to atmospheric composition. The greenhouse periods of Earth's past were sustained by atmospheric carbon dioxide levels that we are rapidly approaching through fossil fuel emissions. While the specific mechanisms that drove prehistoric volcanism are not active today, the atmospheric and oceanic responses to elevated greenhouse gas concentrations remain fundamentally similar. Modern climate models struggle to fully reproduce the extreme conditions documented in the prehistoric record. This isn't because the physics is wrong, but because the computational challenges of modeling such extreme climate states push the boundaries of current technology. The temperature gradients, circulation patterns, and chemical processes that operated during greenhouse periods were so different from modern conditions that they require entirely new modeling approaches. Recent advances in paleoclimate reconstruction have begun to fill in crucial details about these prehistoric climate extremes. Ice core records, marine sediment cores, and terrestrial deposits provide increasingly detailed pictures of how these extreme climate states developed, persisted, and eventually collapsed. These records reveal that transitions between climate states were often rapid and highly nonlinear, with small changes in atmospheric composition triggering dramatic reorganizations of the entire climate system. The implications of this research extend far beyond academic interest. Understanding how Earth's climate system behaved during periods of elevated atmospheric carbon dioxide provides crucial insights into potential future climate scenarios. While we're not likely to see the extreme volcanic activity that drove Mesozoic sea levels, the atmospheric and oceanic responses to greenhouse gas emissions follow similar physical principles. The prehistoric record also reveals that climate system transitions can happen much faster than previously thought. The collapse of ice sheets, the reorganization of ocean circulation, and the shift between different climate states can occur on timescales of centuries to millennia, rather than millions of years. This has profound implications for understanding the potential pace of future climate change and the timeframes over which human societies might need to adapt to changing conditions. Perhaps most importantly, the study of prehistoric sea levels reveals the true range of Earth's climate sensitivity and demonstrates that the stable conditions of recent geological history represent just one possible configuration of our planet's environmental systems. The extreme sea levels we've explored weren't anomalies or temporary deviations. They were stable climate states that persisted for millions of years, reshaping continents and reorganizing global ecosystems on scales that dwarf any changes in human history. These extreme prehistoric sea levels force us to confront an uncomfortable reality about our planet's future. The geological record doesn't just tell us what happened millions of years ago. It provides a roadmap for understanding what could happen again if atmospheric conditions return to prehistoric levels. And the sobering truth is that human activities are pushing atmospheric carbon dioxide concentrations toward levels not seen since these ancient greenhouse periods. Current atmospheric carbon dioxide levels have already exceeded 420 parts per million, approaching concentrations that sustained moderate warming periods in the geological past. But some of the extreme greenhouse episodes we've explored occurred when atmospheric CO2 reached 1,000 to 1,500 parts per million. At current emission rates, such concentrations aren't just possible. They're inevitable unless dramatic changes occur in how human societies produce and consume energy. The prehistoric record suggests that once atmospheric greenhouse gas concentrations cross certain thresholds, the climate system can undergo rapid and irreversible transitions. The Paleocene-Eocene thermal maximum demonstrates that even geologically brief carbon injections can trigger warming episodes that persist for hundreds of thousands of years. The difference is that natural carbon releases occurred over thousands to millions of years, while human emissions are happening over decades to centuries. This compression of timescales creates unprecedented challenges for Earth's climate system. Ice sheets that took millions of years to form during the transition to icehouse conditions could potentially collapse in centuries under rapid warming. Ocean circulation patterns that developed over geological timescales could reorganize within decades. Marine ecosystems that evolved under stable conditions could face environmental changes faster than their ability to adapt. But the prehistoric record also reveals something crucial about the mechanisms that could drive future sea level rise. The complete melting of current ice sheets would raise sea levels by approximately 70 meters. But the geological evidence shows that prehistoric sea levels reached heights of 250 meters above present levels. This means that future warming could potentially activate the same oceanic displacement and thermal expansion mechanisms that operated during ancient greenhouse periods. Modern volcanic activity operates at levels far below prehistoric extremes, but other processes could produce similar effects. The thermal expansion of seawater becomes increasingly powerful as ocean temperatures rise. Current projections suggest that thermal expansion alone could contribute several meters to sea level rise over the coming centuries. But during prehistoric greenhouse periods, thermal expansion contributed tens of meters to sea level elevation. The key difference lies in the magnitude and duration of warming. Current climate projections focus on warming of 2 to 5 degrees Celsius over the next century. But prehistoric greenhouse periods involved sustained warming of 8 to 12 degrees Celsius that persisted for millions of years. At such extreme temperatures, thermal expansion effects become dramatically amplified, contributing to sea level rise on scales that dwarf current projections. Ocean circulation patterns provide another mechanism through which future warming could trigger dramatic sea level changes. The breakdown of modern oceanic circulation during prehistoric greenhouse periods wasn't just an interesting scientific curiosity. It represented a fundamental reorganization of how heat was distributed throughout the global ocean system. If current warming trends disrupt key circulation patterns like the Atlantic meridional overturning circulation, the resulting changes in heat distribution could accelerate both thermal expansion and ice sheet melting. The prehistoric development of oceanic anoxic events also provides sobering insights into potential future ocean conditions. When ocean circulation slows down and stratification increases, vast regions of the ocean can become depleted in oxygen. This doesn't just affect marine life. It fundamentally alters the chemistry of seawater and the ocean's ability to absorb atmospheric carbon dioxide. Modern oceans currently absorb approximately 25% of human carbon dioxide emissions, helping to moderate the rate of atmospheric accumulation. But during prehistoric oceanic anoxic events, this carbon absorption capacity was severely reduced. If future warming triggers similar oceanic conditions, the rate of atmospheric carbon dioxide accumulation could accelerate dramatically, creating a feedback loop that amplifies warming beyond current projections. The biological implications of returning to prehistoric oceanic conditions extend far beyond simple temperature increases. Modern marine ecosystems evolved during the relatively stable icehouse conditions of the past 30 million years. These ecosystems are adapted to temperature ranges, acidity levels, and circulation patterns that have remained relatively constant throughout their evolutionary history. Prehistoric marine ecosystems operated under completely different conditions, dominated by organisms that could tolerate extreme temperatures and chemical compositions. The transition between these ecosystem types wasn't gradual. The fossil record shows that marine ecosystem collapses and reorganizations could occur over thousands rather than millions of years. Current marine ecosystems are already showing signs of stress from relatively modest warming and acidification. Coral reef bleaching, shifts in fish populations, and changes in plankton communities all suggest that modern marine life is approaching the limits of its environmental tolerance. A transition to prehistoric oceanic conditions would likely require a complete reorganization of marine ecosystems, with consequences that cascade throughout global food webs. The terrestrial implications of returning to prehistoric sea levels are equally dramatic. Current coastal infrastructure, agricultural systems, and human settlements are all located based on the assumption that sea levels will remain relatively stable. Even modest sea level rise of 1 to 2 meters would displace hundreds of millions of people and inundate vast areas of agricultural land. But prehistoric sea levels reached heights that would completely transform global geography. Coastal plains that currently support billions of people and produce much of the world's food would disappear beneath shallow seas. River deltas that form the agricultural heartlands of major civilizations would be submerged. Entire nations built on low-lying terrain would cease to exist. The speed of these changes represents perhaps the greatest challenge. Prehistoric transitions to high sea level conditions occurred over millions of years, allowing biological and geological systems time to adjust. But human-induced warming is happening at speeds that compress these transitions into centuries or millennia. This leaves little time for natural adaptation processes to operate effectively. Coastal ecosystems provide a particularly striking example of this compression effect. Salt marshes, mangrove forests, and coastal wetlands can migrate inland as sea levels rise, but only if the rate of change allows them to establish new populations faster than existing habitats are submerged. Rapid sea level rise can outpace these migration processes, leading to ecosystem collapse rather than adaptation. The geological evidence for rapid sea level changes during prehistoric warming episodes provides sobering insights into potential future scenarios. Meltwater pulse events preserved in the rock record show that ice sheets can collapse much faster than their long-term melting rates would suggest. These rapid collapse events could raise sea levels by several meters in just decades to centuries. The West Antarctic ice sheet represents a particularly vulnerable component of the current ice budget. This ice sheet sits on bedrock that lies below sea level, making it susceptible to rapid collapse if warming ocean waters penetrate beneath the ice. Geological evidence suggests that this ice sheet has collapsed completely during previous warm periods, contributing approximately 3 to 4 meters to global sea level rise. The Greenland ice sheet presents a different but equally concerning vulnerability. Surface melting on this ice sheet has accelerated dramatically over recent decades, creating feedback loops that could lead to complete ice sheet loss over centuries to millennia. The geological record shows that Greenland was largely ice-free during previous warm periods, contributing approximately 7 meters to global sea level rise. But even complete melting of current ice sheets only accounts for about 70 meters of potential sea level rise. The geological record shows that prehistoric sea levels reached heights that require additional mechanisms beyond simple ice melting. Understanding these mechanisms becomes crucial for evaluating long-term sea level projections under continued warming. The relationship between atmospheric carbon dioxide levels and sea level response reveals important insights about climate system sensitivity. During the Pliocene period, atmospheric CO2 levels similar to today's supported sea levels, 22 meters higher than present. This suggests that current atmospheric conditions may already be sufficient to trigger substantial long-term sea level rise, even without additional emissions. The lag time between atmospheric changes and sea level response represents a crucial factor in understanding future scenarios. Ice sheets respond to warming over timescales of centuries to millennia, while thermal expansion of seawater occurs over decades to centuries. This means that even if greenhouse gas emissions were stabilized immediately, sea level rise would continue for hundreds to thousands of years as the climate system adjusts to current atmospheric conditions. Paleoclimate reconstructions also reveal the importance of tipping points in the climate system. Small changes in atmospheric composition can trigger large changes in sea level if they push the system past critical thresholds. The rapid warming of the Paleocene-Eocene thermal maximum shows that these thresholds can be crossed quickly once atmospheric conditions reach certain levels. The geographic distribution of prehistoric sea level changes provides insights into regional variations in future sea level rise. During ancient high sea level periods, the pattern of marine inundation wasn't uniform across the globe. Some regions experienced sea level rise greater than the global average, while others saw smaller increases due to factors like regional ocean circulation patterns and local geological processes. Modern sea level rise already shows similar regional variations, with some coastal areas experiencing rise rates several times the global average. Understanding how these regional patterns developed during prehistoric high sea level periods could improve projections of future regional sea level changes and help identify particularly vulnerable coastal areas. The economic implications of returning to prehistoric sea level conditions extend far beyond the direct costs of coastal flooding. Global trade networks, agricultural systems, and industrial infrastructure are all concentrated in coastal regions that would be transformed by substantial sea level rise. The relocation of populations and economic activities on scales suggested by prehistoric sea levels would represent one of the largest reorganizations in human history. Current estimates of sea level rise costs focus on relatively modest scenarios of 1 to 2 meters of rise over the coming century, but prehistoric sea levels suggest that much larger changes are possible if warming continues unabated. The costs of adapting to or relocating from sea level rise measured in tens of meters would likely exceed the total economic output of many nations. The social and political implications of prehistoric scale sea level changes are equally staggering. Mass migrations triggered by coastal inundation could destabilize entire regions and create conflicts over remaining habitable land and resources. The breakdown of existing political boundaries and economic systems could trigger social upheaval on scales unprecedented in human history. International cooperation becomes crucial for managing transitions of this magnitude. The prehistoric record shows that environmental changes on this scale affect all regions simultaneously, making isolated national responses inadequate. Coordination of adaptation strategies, resource sharing, and population relocations would require levels of international cooperation that exceed current institutional capacities. The technological challenges of adapting to prehistoric scale sea level changes also exceed current capabilities. Engineering solutions like seawalls and flood barriers become impractical when dealing with sea level rise measured in tens of meters. Relocation strategies require the development of new cities and infrastructure systems on scales and timescales that challenge current planning and construction capabilities. Agricultural implications represent another critical challenge. Much of the world's most productive agricultural land lies in coastal plains and river deltas that would be submerged by prehistoric scale sea level rise. Replacing this agricultural capacity would require the development of new farming systems in regions that currently support lower productivity agriculture or natural ecosystems. The freshwater implications of extreme sea level rise extend beyond simple land loss. Coastal aquifers that currently provide freshwater for billions of people would become contaminated by saltwater intrusion. River systems would be fundamentally altered as their mouths move inland and their flow patterns adjust to new base levels. Urban planning for prehistoric scale sea level scenarios requires completely reimagining how human societies organize themselves geographically. Current cities developed around assumptions of stable coastlines and predictable river systems. Adapting urban systems to prehistoric oceanic conditions would likely require abandoning many existing population centers and developing new models of settlement that can accommodate dynamic coastal environments. The cultural implications of such dramatic geographic changes extend beyond practical considerations. Many human cultures have developed deep connections to specific coastal landscapes and marine environments. The loss of these landscapes to rising seas would represent cultural disruptions comparable to the environmental changes themselves. Historical precedents for managing environmental changes of this magnitude are limited. While human societies have adapted to significant environmental changes throughout history, none approach the scale and speed of the transitions suggested by prehistoric sea level scenarios. This lack of precedent makes it difficult to predict how societies might adapt or what institutions and technologies would prove most effective. The prehistoric record does provide some insights into biological and ecological responses to extreme environmental change. During previous transitions to greenhouse conditions, many species went extinct, while others radiated into new ecological niches. Understanding these patterns could help predict which components of modern ecosystems are most vulnerable and which might prove most adaptable. Conservation strategies for managing transitions to prehistoric environmental conditions require fundamentally different approaches than current conservation methods. Instead of trying to preserve existing ecosystems in their current locations, conservation efforts might need to focus on facilitating ecosystem migration and adaptation to new environmental conditions. The energy implications of adapting to prehistoric scale environmental changes also present significant challenges. Current renewable energy technologies depend on materials and manufacturing processes that could be disrupted by dramatic environmental changes. Developing energy systems that remain functional under prehistoric environmental conditions requires anticipating and planning for disruptions that exceed current experience. Research priorities for understanding these potential futures increasingly focus on improving paleoclimate reconstructions and developing better models of climate system behavior under extreme conditions. The prehistoric record provides crucial data for testing and improving climate models, but significant gaps remain in understanding the detailed mechanisms that operated during ancient greenhouse periods. International scientific cooperation becomes essential for advancing this research. The global nature of prehistoric climate changes means that evidence is preserved in geological formations around the world. Coordinating research efforts across different regions and disciplines is necessary for developing comprehensive understanding of these ancient climate systems. The urgency of this research stems from the rapid pace of current environmental change. While prehistoric transitions to greenhouse conditions occurred over millions of years, human activities are pushing atmospheric composition toward prehistoric levels over decades to centuries. This compression of timescales means that understanding gained from paleoclimate research must be applied quickly to inform current decision-making. Educational implications of prehistoric climate research extend beyond scientific communities. public understanding of the potential for dramatic environmental change remains limited, partly because the scale of prehistoric changes exceeds everyday experience. Communicating the implications of paleoclimate research requires developing new ways to help people understand environmental changes that operate on spatial and temporal scales far beyond human experience. The prehistoric record ultimately reveals that the stable environmental conditions of recent human history represent just one possible state of Earth's climate system. The extreme sea levels we've explored weren't anomalies or temporary deviations from normal conditions. They were stable climate states that persisted for millions of years, supported complex ecosystems, and operated according to physical principles that remain active today. Understanding these prehistoric extremes doesn't provide simple answers about future environmental change, but it does reveal the true range of possibilities that Earth's climate system can produce. The mechanisms that drove prehistoric sea levels to heights of 250 meters above present levels haven't disappeared. They're simply dormant, waiting for atmospheric conditions that could reactivate them. The geological record serves as both a warning and a guide for navigating potential future environmental changes. It warns us that the climate system can undergo transitions far more dramatic than anything in human experience. But it also provides crucial information about how these transitions occur, how long they persist, and what factors control their development and eventual resolution. Human societies now face the challenge of making decisions about energy systems, infrastructure, and social organization, while confronting the possibility of environmental changes that exceed all historical precedent. The prehistoric record provides essential context for understanding these challenges, revealing both the potential magnitude of future changes and the physical processes that could drive them. The extreme sea levels of Earth's prehistoric past remind us that our planet has operated under conditions far different from those that shaped human civilization. These ancient oceanic extremes challenge us to think beyond the comfortable assumptions of environmental stability and to prepare for futures that may bear little resemblance to the world we know today. The story of prehistoric sea levels becomes even more extraordinary when we examine the role of continental configuration in amplifying these oceanic extremes. During the periods of higher sea levels, the continents themselves were positioned in ways that maximize the impact of rising waters. Unlike today's world, where large landmasses are distributed across different latitudes, prehistoric continents were often clustered near the equator or arranged in patterns that created vast, unobstructed oceanic basins. Consider the continental arrangement during the Cretaceous period. The supercontinent Pangaea had already begun breaking apart, but the resulting continental fragments were positioned to create enormous interior seaways. North America was split nearly in half by the Western Interior Seaway, a marine corridor that stretched from the Gulf of Mexico to the Arctic Ocean. This wasn't simply a flooded river valley or a temporary lake. This was a genuine oceanic environment, complete with marine currents, tidal systems, and deep water circulation patterns. The Western Interior Seaway reached widths of over 1,000 kilometers at its maximum extent, creating what was essentially an inland ocean in the heart of North America. The seaway was so large that it influenced regional climate patterns, creating its own weather systems and supporting marine ecosystems that rivaled those of the open ocean. Fossil evidence from the seaway includes massive marine reptiles like Tylosaurus, a mosasaur that reached lengths of over 15 meters, demonstrating that these inland seas supported top predators as large as any found in modern oceans. But North America wasn't unique in this regard. Similar continental configurations created inland seas across the globe during periods of extreme sea level elevation. The Tethys Ocean, a massive equatorial seaway that separated the northern and southern continents during much of the Mesozoic, created marine connections that spanned from the Atlantic to the Pacific. This oceanic corridor was so extensive that it functioned as a marine highway, allowing the migration of marine organisms across vast distances and creating remarkably uniform oceanic conditions across multiple continents. The European continent during the Cretaceous was transformed into an archipelago of tropical islands separated by warm, shallow seas. The familiar geography of modern Europe simply didn't exist. Instead, limestone formations across the continent preserve evidence of coral reefs, tropical marine communities, and warm water circulation patterns that extended far into what are now temperate latitudes. These continental configurations weren't just passive recipients of rising sea levels. They actively amplified the effects of oceanic expansion through a process scientists call continental flooding feedback. When ocean waters flooded across low-lying continental areas, they created vast, shallow seas that absorbed enormous amounts of solar energy. These shallow marine environments heated up much more efficiently than deep ocean basins, contributing additional thermal expansion effects that push sea levels even higher. The physics of this process are straightforward but powerful. Shallow water heats up faster and to higher temperatures than deep water because there's less volume to absorb the same amount of solar energy. During prehistoric periods when continental flooding was extensive, these shallow seas could reach temperatures approaching 40 degrees Celsius, well above the temperature of even tropical surface waters in modern deep oceans. These superheated shallow seas didn't just contribute to thermal expansion, they also created powerful evaporation effects that pumped enormous amounts of water vapor into the atmosphere. Water vapor is itself a potent greenhouse gas, creating additional warming that further enhanced thermal expansion and ice melting. This created a feedback loop where continental flooding led to enhanced heating, which led to higher sea levels, which led to more continental flooding. The geological evidence for these continental flooding effects is preserved in sedimentary formations that span entire continents. The chalk deposits that give the Cretaceous period its name formed in these extensive shallow seas, created by massive blooms of microscopic marine organisms that thrived in the warm, nutrient-rich waters. The thickness and extent of these chalk formations provide direct evidence of how long these shallow marine conditions persisted and how productive these unusual oceanic environments were. The Niobrara Formation of the western United States preserves one of the most complete records of life in these prehistoric inland seas. This geological formation extends from Kansas to Montana, representing millions of years of deposition in the western interior seaway. The fossils preserved in the Niobrara include not just marine reptiles and fish, but also microscopic organisms that reveal the detailed chemistry and temperature conditions of these ancient waters. Chemical analysis of these fossils indicates ocean temperatures that would be lethal to most modern marine life. Oxygen isotope ratios in fossil shells suggest surface water temperatures regularly exceeded 35 degrees Celsius, with some estimates reaching as high as 40 degrees in shallow areas. These aren't brief temperature spikes or seasonal extremes. These were sustained temperature conditions that persisted for millions of years. The biological communities that thrived under these extreme conditions were unlike anything in the modern world. Instead of the diverse, complex ecosystems we see in today's oceans, prehistoric shallow seas were often dominated by a few highly specialized species that could tolerate extreme temperatures and chemical conditions. Massive blooms of single-celled organisms created what scientists call carbonate factories, biological systems that produce limestone at rates far exceeding anything observed in modern marine environments. These carbonate-producing organisms weren't just creating pretty shells. They were fundamentally altering ocean chemistry by removing enormous quantities of carbon dioxide from seawater and atmosphere. The limestone formations they created represent one of the largest carbon sinks in Earth's history, temporarily storing atmospheric carbon in solid rock formations. But this carbon storage came with a cost, as the biological processes involved in carbonate production also released other greenhouse gases and altered seawater chemistry in ways that could trigger additional environmental changes. The collapse of these extensive shallow sea systems provides crucial insights into how prehistoric high sea level conditions eventually ended. As continental positions shifted and volcanic activity waned, the shallow seas that had amplified warming effects began to drain. This wasn't a gradual process. Geological evidence suggests that the retreat of these inland seas could happen relatively quickly once the underlying drivers of sea level elevation began to weaken. The draining of the western interior seaway, for example, occurred over just a few million years as sea levels dropped and continental uplift exposed former seafloor areas. But this transition wasn't smooth. Instead, it was marked by dramatic fluctuations in sea level, with the seaway repeatedly flooding and draining as the climate systems struggled to find a new equilibrium. These transitions reveal something crucial about the stability of extreme sea level conditions. While prehistoric high sea levels could persist for millions of years, they were ultimately dependent on maintaining very specific atmospheric, volcanic, and continental conditions. When any of these factors changed significantly, the entire system could collapse relatively quickly, leading to dramatic reorganizations of global climate and sea level patterns. The role of atmospheric circulation in maintaining extreme sea level conditions provides another key piece of the prehistoric puzzle. During periods of maximum sea level elevation, atmospheric circulation patterns were fundamentally different from those we observe today. The absence of polar ice caps and the presence of extensive tropical seas created atmospheric conditions that enhanced the greenhouse effect far beyond what elevated carbon dioxide levels alone could achieve. Without polar ice caps to create strong temperature gradients between equator and poles, atmospheric circulation patterns became much more sluggish and less efficient at distributing heat around the globe. This led to the development of what scientists call equable climates, where temperature differences between tropical and polar regions were much smaller than today. While this might sound pleasant, these equable conditions actually enhanced warming effects by preventing the efficient cooling that occurs when hot tropical air mixes with cold polar air masses. The atmospheric circulation patterns of prehistoric greenhouse periods also created conditions that favored the persistence of extreme weather events. Without strong jet streams and polar vortices to break up weather systems, heat waves, storms, and other extreme events could persist for much longer periods than in the modern world. This enhanced the warming effects of greenhouse gas concentrations and created additional stress on marine and terrestrial ecosystems. Modern climate models struggle to fully reproduce these atmospheric circulation patterns because they operate under conditions so different from anything in recent Earth history. The computational challenges of modeling atmospheric circulation without polar ice caps, with extensive shallow seas, and under extreme greenhouse gas concentrations push current climate models to their limits. Recent advances in paleoclimate modeling have begun to provide insights into how these atmospheric systems functioned, but significant gaps remain in our understanding. The interaction between atmospheric circulation, oceanic circulation, and continental flooding during prehistoric greenhouse periods involved complex feedback loops that are only beginning to be understood. The implications of these atmospheric circulation changes extend far beyond academic interest. Understanding how atmospheric patterns respond to extreme greenhouse conditions provides crucial insights into potential future climate scenarios. Current climate projections assume that atmospheric circulation patterns will remain relatively similar to today's, but the prehistoric record suggests that substantial warming could trigger fundamental reorganizations of atmospheric circulation. The breakdown of modern atmospheric circulation patterns could have dramatic effects on regional climate conditions, ocean currents, and the distribution of precipitation around the globe. The equable climates of prehistoric greenhouse periods weren't just warmer than today, they were characterized by completely different patterns of seasonal variation, storm systems, and regional climate conditions. These circulation changes also affected the distribution of moisture and precipitation in ways that amplified sea level rise. Enhanced evaporation from extensive warm seas pumped enormous amounts of water vapor into the atmosphere. But the sluggish circulation patterns of greenhouse climates meant that this moisture often remained in the atmosphere for extended periods, rather than quickly condensing and returning to the surface. This enhanced atmospheric moisture content created additional greenhouse warming through water vapor feedback effects. Water vapor is a potent greenhouse gas, and the high atmospheric humidity of prehistoric greenhouse periods contributed significantly to maintaining the extreme temperatures that drove thermal expansion and ice melting. The chemical composition of prehistoric atmospheres during high sea level periods also differed dramatically from modern conditions. Beyond simply having higher carbon dioxide concentrations, these atmospheres contained elevated levels of methane, sulfur compounds, and other trace gases that enhanced greenhouse effects and altered atmospheric chemistry. Massive volcanic episodes that contributed to prehistoric sea level rise also released enormous quantities of sulfur dioxide into the atmosphere. While sulfur compounds can have cooling effects by reflecting sunlight back to space, they also create acid rain conditions that alter surface water chemistry and can trigger additional greenhouse gas releases from soils and sediments. The methane content of prehistoric atmospheres during greenhouse periods was likely much higher than today due to enhanced biological activity in warm, oxygen-poor marine environments and wetlands. Methanogenic bacteria thrive in warm, anoxic conditions, and the extensive shallow seas and coastal wetlands of prehistoric high sea level periods would have provided ideal conditions for enhanced methane production. These elevated methane concentrations created additional warming beyond that caused by carbon dioxide alone. Methane is a much more potent greenhouse gas than carbon dioxide on short timescales, and elevated atmospheric methane during prehistoric periods could have contributed several degrees of additional warming. The interaction between different atmospheric greenhouse gases during prehistoric periods created complex feedback loops that amplified warming effects. Higher temperatures increased biological methane production, which enhanced warming, which increased evaporation and atmospheric water vapor content, which further enhanced warming. These feedback loops help explain how prehistoric greenhouse conditions could be sustained for millions of years once they became established. Understanding these atmospheric chemistry effects becomes crucial for evaluating potential future climate scenarios. Current climate projections focus primarily on carbon dioxide effects, but the prehistoric record suggests that other greenhouse gases could play increasingly important roles as warming progresses. Enhanced methane emissions from warming permafrost, changing agricultural practices, and altered marine ecosystems could recreate some of the atmospheric chemistry conditions that sustained prehistoric greenhouse climates. While modern methane sources differ from those of prehistoric periods, the physical and chemical processes that amplify greenhouse effects remain fundamentally similar. The role of clouds and atmospheric aerosols during prehistoric greenhouse periods represents another area where current understanding remains limited. Cloud formation and behavior under extreme greenhouse conditions would have differed substantially from modern patterns, potentially creating additional feedback effects that enhanced or moderated warming. High atmospheric humidity and altered circulation patterns during prehistoric greenhouse periods would have created cloud systems unlike anything observed in the modern world. These cloud systems could have had complex effects on surface temperatures, with some regions experiencing enhanced warming due to increased water vapor, while others experienced cooling due to increased cloud cover. The volcanic activity that contributed to prehistoric sea level rise also injected enormous quantities of aerosols into the atmosphere. These aerosols can have both warming and cooling effects depending on their composition and altitude, creating complex interactions with greenhouse gas effects that are difficult to model accurately. Recent research into prehistoric atmospheric conditions has begun to provide more detailed insights into these complex interactions. Ice core records, marine sediment cores, and terrestrial deposits preserve chemical signatures that reveal atmospheric composition during prehistoric greenhouse periods. These records show that atmospheric chemistry during high sea level periods was far more complex than simple elevations in carbon dioxide concentrations. The isotopic composition of atmospheric gases preserved in ancient air bubbles reveals information about the sources and cycling of different greenhouse gases during prehistoric periods. This research has shown that biological processes played much larger roles in atmospheric chemistry during greenhouse periods than they do today, partly due to the enhanced biological productivity of warm, extensive marine environments. The sulfur isotope signatures preserved in prehistoric sediments reveal information about volcanic activity and atmospheric sulfur cycling during greenhouse periods. These records show that volcanic sulfur emissions during prehistoric high sea level periods were not just larger in scale than modern emissions, but also different in composition and timing. Understanding the detailed atmospheric chemistry of prehistoric greenhouse periods provides crucial context for interpreting current atmospheric changes. While modern greenhouse gas sources differ from those of prehistoric periods, the atmospheric and climatic responses to elevated greenhouse gas concentrations follow similar physical principles. The rate of change represents perhaps the most significant difference between prehistoric and modern atmospheric changes. Prehistoric greenhouse conditions developed over millions of years, allowing atmospheric chemistry to reach equilibrium with oceanic and biological systems. Modern greenhouse gas emissions are occurring over decades to centuries, creating atmospheric disequilibrium that could lead to more rapid and extreme responses. This compression of timescales means that modern climate responses might overshoot the equilibrium conditions suggested by prehistoric analogues. The atmospheric and oceanic systems that sustained prehistoric greenhouse conditions had millions of years to develop stable feedback loops and circulation patterns. Modern rapid emissions could trigger responses that exceed prehistoric extremes before stabilizing feedback mechanisms have time to develop. The biological implications of returning to prehistoric atmospheric chemistry extend far beyond simple temperature effects. Many modern organisms evolved under the relatively stable atmospheric conditions of recent icehouse climates. Rapid changes in atmospheric composition could stress these organisms beyond their adaptive capacity, leading to ecosystem collapses that differ from the gradual transitions observed in the prehistoric record. Modern agricultural systems represent a particularly vulnerable component of human society under scenarios of rapid atmospheric change. Crop plants have been bred for optimal performance under current atmospheric and climatic conditions. Rapid changes in atmospheric chemistry, temperature, and precipitation patterns could severely impact agricultural productivity before new crop varieties can be developed and deployed. The technological implications of prehistoric atmospheric chemistry scenarios also present significant challenges. Many modern technologies, from solar panels to computer systems, are designed to operate under current atmospheric conditions. Changes in atmospheric composition, humidity, and temperature could affect the performance and durability of these systems in ways that are difficult to predict or prepare for. Materials science becomes crucial for developing technologies that can function under prehistoric atmospheric chemistry conditions. Elevated humidity, altered precipitation chemistry, and enhanced atmospheric reactivity could accelerate corrosion and degradation of many modern materials. Understanding how prehistoric organisms and geological systems responded to these conditions could provide insights for developing more resilient technologies. The preservation of infrastructure and cultural artifacts under prehistoric atmospheric conditions represents another significant challenge. Many materials that we rely on for preserving information and cultural heritage are vulnerable to the chemical conditions that characterize prehistoric atmospheres. Planning for long-term preservation requires anticipating environmental changes that exceed current experience. The social implications of transitioning to prehistoric atmospheric chemistry extend beyond technological challenges. Human societies have never experienced atmospheric conditions comparable to prehistoric greenhouse periods. The psychological and cultural effects of living under such dramatically different environmental conditions are difficult to predict, but could be profound. Air quality under prehistoric atmospheric conditions would likely differ substantially from current standards. Higher humidity, elevated reactive gas concentrations, and altered precipitation chemistry could create air quality challenges that exceed current pollution concerns. Understanding and preparing for these changes requires research into atmospheric chemistry effects that go far beyond current air quality monitoring. The health implications of prehistoric atmospheric chemistry also require consideration. Human respiratory and circulatory systems evolved under current atmospheric conditions and might not function optimally under the elevated humidity, altered gas concentrations, and enhanced atmospheric reactivity of prehistoric greenhouse periods. Water quality represents another area where prehistoric atmospheric chemistry could create significant challenges. Acid rain from volcanic sulfur emissions and altered precipitation chemistry from enhanced atmospheric reactivity could affect fresh water supplies in ways that exceed current water treatment capabilities. The agricultural implications extend beyond simple crop performance to include soil chemistry changes under prehistoric atmospheric conditions. Enhanced atmospheric reactivity and altered precipitation chemistry could change soil pH, nutrient availability, and biological activity in ways that affect agricultural productivity beyond direct climate effects. Ecosystem services that modern societies depend on could also be affected by transitions to prehistoric atmospheric chemistry. Natural water filtration, air purification, and climate regulation provided by ecosystems might function differently under prehistoric atmospheric conditions, requiring the development of technological alternatives or enhanced ecosystem management strategies. The economic implications of transitioning to prehistoric atmospheric chemistry involve costs that extend far beyond current climate change estimates. Adapting infrastructure, agriculture, and technology to function under prehistoric atmospheric conditions could require economic investments that exceed the total economic output of many nations. International cooperation becomes essential for managing transitions to prehistoric atmospheric chemistry because these changes would affect all regions simultaneously. Coordinating responses to atmospheric chemistry, changes that exceed current experience, would require unprecedented levels of international scientific and technical cooperation. Research priorities for understanding prehistoric atmospheric chemistry increasingly focus on developing better models of atmospheric behavior under extreme greenhouse conditions. Current atmospheric chemistry models are calibrated for modern conditions and may not accurately predict behavior under prehistoric greenhouse scenarios. Laboratory studies of atmospheric chemistry under prehistoric conditions provide crucial data for improving these models. Experimental simulations of prehistoric atmospheric compositions, temperatures, and humidity levels can reveal chemical reactions and processes that don't occur under current conditions. The integration of paleoclimate data with modern atmospheric chemistry research represents a rapidly growing field that combines geological evidence with laboratory experiments and computational modeling. This interdisciplinary approach is essential for understanding how atmospheric systems function under conditions outside the range of modern experience. Educational implications of prehistoric atmospheric chemistry research extend to public understanding of potential future environmental changes. Communicating the implications of atmospheric chemistry, changes that exceed current experience, requires developing new approaches to environmental education and public engagement. The urgency of this research stems from the rapid pace of current atmospheric changes. While prehistoric transitions to extreme atmospheric chemistry occurred over millions of years, modern emissions are pushing atmospheric composition toward prehistoric levels over decades to centuries. This means that research into prehistoric atmospheric chemistry must be applied quickly to inform current decision-making about emissions and adaptation strategies. The prehistoric record ultimately reveals that Earth's atmospheric chemistry can operate in modes far different from current conditions. The atmospheric compositions that sustained prehistoric high sea levels weren't temporary anomalies, but stable chemical states that persisted for millions of years. Understanding these atmospheric systems provides crucial insights into potential future scenarios and the challenges of adapting human societies to atmospheric changes that exceed all historical precedent. The interconnected nature of these atmospheric and oceanic systems during prehistoric greenhouse periods reveals just how dramatically different Earth's environmental machinery operated when running at full throttle. But there's another layer to this story that makes these ancient conditions even more remarkable. The way life itself responded to and shaped these extreme environments tells us something profound about the relationship between biology and planetary systems. During the height of Cretaceous sea levels, marine ecosystems weren't just passively responding to environmental extremes. They were actively participating in creating and maintaining the very conditions that sustained these oceanic giants. The microscopic organisms that thrived in superheated shallow seas were essentially biological engines, processing enormous quantities of carbon, sulfur, and other elements in ways that influenced global atmospheric and oceanic chemistry. Consider the scale of biological productivity during these periods. The chalk formations that stretch across multiple continents represent the accumulated remains of countless trillions of microscopic marine organisms called coccolithophores. These tiny creatures, barely visible to the naked eye, were constructing elaborate calcium carbonate shells while living in waters that would instantly kill their modern relatives. But they weren't just surviving. They were flourishing on scales that dwarf anything in today's oceans. The White Cliffs of Dover provide a stunning example of this biological productivity. These towering chalk formations, rising over 100 meters above the English Channel, represent just a small fraction of the Cretaceous marine productivity. Similar chalk deposits extend across Europe, through the Middle East, and into North America, creating a geological testament to marine ecosystems that operated under conditions we can barely imagine. But these weren't the only organisms reshaping prehistoric oceans. Massive coral reefs extended far beyond tropical latitudes, creating limestone platforms in regions that are now temperate or even subarctic. These coral communities were building reef structures in waters approaching 40 degrees Celsius, temperatures that would bleach and kill virtually all modern coral species within days. The fossil record from these prehistoric reefs reveals coral species that had evolved completely different physiological mechanisms for dealing with extreme heat. Instead of the symbiotic relationships with algae that characterize modern corals, many Cretaceous corals appear to have relied on different metabolic pathways that could function efficiently under extreme temperature conditions. These weren't simply larger versions of modern corals. They were fundamentally different organisms adapted to oceanic conditions that no longer exist. The marine reptiles that dominated these prehistoric seas represent another extraordinary example of adaptation to extreme conditions. Mosasaurs like Tylosaurus and Plate Carpus weren't just large marine predators. They were air-breathing vertebrates that had evolved to thrive in oceanic environments with temperatures, chemistry, and circulation patterns completely unlike those of modern seas. These marine reptiles reach sizes that dwarf most modern marine predators. Mosasaurus hoffmanni stretched over 17 meters in length, larger than any modern predatory marine animal except the largest sharks. But size wasn't their only remarkable adaptation. Chemical analysis of fossilized teeth and bones reveals that these creatures were processing nutrients and maintaining body chemistry under oceanic conditions that would be toxic to most modern marine life. The feeding strategies of these prehistoric marine giants also differed dramatically from modern ecosystems. Instead of the complex food webs we see in today's oceans, prehistoric marine communities were often dominated by relatively simple food chains, with enormous primary productivity supporting massive predators. The warm, nutrient-rich waters of prehistoric seas could sustain biological productivity levels that made it possible for marine reptiles to reach sizes that would be impossible in modern oceanic conditions. But perhaps the most remarkable aspect of these prehistoric marine ecosystems was their role in regulating global carbon cycles. The massive productivity of marine organisms wasn't just creating impressive fossil deposits. It was actively removing enormous quantities of carbon dioxide from the atmosphere and oceans, helping to moderate the greenhouse conditions that had created the extreme sea levels in the first place. This biological carbon pump operated on scales that dwarf modern oceanic carbon cycling. During peak productivity periods, marine organisms were sequestering carbon at rates that could measurably affect atmospheric carbon dioxide concentrations. The limestone and chalk formations they created represent one of the largest long-term carbon storage systems in Earth's history, locking away atmospheric carbon for millions of years. However, this biological carbon sequestration came with complex feedback effects. The process of building calcium carbonate shells and skeletons actually releases carbon dioxide as a byproduct, meaning that enhanced marine productivity could sometimes increase rather than decrease atmospheric greenhouse gas concentrations. The balance between these competing effects varied depending on oceanic conditions, biological community composition, and the specific chemical processes involved. The collapse of these extraordinary marine ecosystems provides crucial insights into the vulnerability of biological systems under extreme environmental conditions. Despite their apparent success in adapting to greenhouse oceanic conditions, these prehistoric marine communities were ultimately dependent on maintaining very specific environmental parameters. When oceanic temperatures, chemistry, or circulation patterns shifted beyond certain thresholds, even these highly adapted ecosystems could collapse relatively rapidly. The end Cretaceous extinction event demonstrates just how quickly these seemingly robust biological systems could disintegrate. Within a few 100,000 years, marine ecosystems that had dominated the oceans for tens of millions of years virtually disappeared. The massive marine reptiles, the extensive coral reefs, and the hyperproductive plankton communities all collapsed as oceanic conditions shifted beyond their adaptive limits. This collapse wasn't simply a matter of organisms being unable to tolerate changing conditions. The biological processes that had helped maintain extreme oceanic conditions began operating in reverse, accelerating environmental changes rather than moderating them. As marine productivity declined, less carbon was being removed from the atmosphere, enhancing greenhouse effects. As reef-building organisms died off, the shallow platforms they had created began to subside, altering coastal and oceanic circulation patterns. The lesson here extends far beyond prehistoric curiosity. These ancient marine ecosystems demonstrate that biological systems can adapt to environmental conditions far more extreme than anything in modern experience. But they also show that such adaptations can be highly specialized and vulnerable to rapid environmental change. The biological communities that thrived under prehistoric greenhouse conditions weren't simply tougher versions of modern organisms. They were fundamentally different biological systems adapted to environmental conditions that required completely different evolutionary strategies. Modern marine ecosystems face a troubling parallel to these prehistoric transitions. Current rates of oceanic warming, acidification, and chemical change are approaching speeds that exceed the adaptive capacity of many marine organisms. Unlike the gradual transitions that allowed prehistoric organisms millions of years to adapt to extreme conditions, modern environmental changes are happening over decades to centuries. The implications extend to terrestrial ecosystems as well. During periods of maximum sea level elevation, the boundaries between marine and terrestrial environments became highly dynamic. Coastal wetlands, estuaries, and river deltas extended far inland, creating transitional ecosystems that supported biological communities unlike anything in the modern world. These transitional environments play crucial roles in global biogeochemical cycles, processing enormous quantities of nutrients, carbon, and other elements as they move between terrestrial and marine systems. The chemical signatures preserved in prehistoric sediments reveal that these coastal transitional zones were among the most biologically active and chemically dynamic environments on the planet. The scale of these transitional ecosystems was staggering. During Cretaceous high sea level periods, coastal wetlands extended hundreds of kilometers inland along major river systems. These weren't narrow strips of marshy terrain like modern coastal wetlands. They were vast, continent-spanning ecosystems that covered areas larger than many modern countries. The biological productivity of these extensive coastal systems contributed significantly to global carbon cycling and atmospheric chemistry. Wetland plants and microorganisms were processing organic matter under conditions of elevated temperature, humidity, and atmospheric carbon dioxide that enhanced photosynthesis and biological activity far beyond modern levels. But these enhanced biological processes also created conditions for massive greenhouse gas production. Warm, waterlogged soils in extensive wetland systems are ideal environments for methanogenic bacteria that produce methane as a byproduct of organic matter decomposition. The vast coastal wetlands of prehistoric high sea level periods were likely major sources of atmospheric methane, contributing to the greenhouse conditions that sustained extreme sea levels. The interaction between these biological methane sources and atmospheric chemistry created complex feedback loops that could either enhance or moderate greenhouse conditions depending on other environmental factors. Enhanced methane production contributed to atmospheric warming, but increased plant productivity in warm carbon dioxide. Rich conditions also removed carbon dioxide from the atmosphere through photosynthesis. The balance between these competing biological effects varied over time and geography, creating dynamic patterns of greenhouse gas production and consumption that influenced regional and global climate conditions. Understanding these biological feedback loops becomes crucial for predicting how modern ecosystems might respond to rapid environmental change. The fossil record from these extensive prehistoric wetland systems preserves evidence of plant and animal communities that were adapted to environmental conditions far outside the range of modern experience. Giant ferns, massive conifer trees, and early flowering plants created forest ecosystems in regions that would be completely submerged under current sea levels. These prehistoric forests weren't simply larger versions of modern vegetation. They were biological communities adapted to growing in soils that were periodically inundated by marine waters, under atmospheric conditions with carbon dioxide concentrations several times higher than today, and in climatic conditions where seasonal temperature variations were much smaller than modern patterns. The physiological adaptations required for plants to thrive under these conditions involved fundamental changes in photosynthesis, water regulation, and nutrient processing. Many prehistoric plants developed specialized structures for dealing with saltwater intrusion, enhanced carbon dioxide concentrations, and the extreme humidity of greenhouse climatic conditions. Animal communities in these prehistoric coastal ecosystems were equally remarkable. Early mammals, primitive birds, and diverse reptile communities shared habitats that shifted dynamically between terrestrial and marine conditions. These animals had to be capable of surviving periodic flooding, extreme humidity, and temperature conditions that would stress most modern terrestrial species beyond their adaptive limits. The evolutionary innovations that emerged in these dynamic coastal environments had lasting impacts on the history of life. Many of the physiological and behavioral adaptations that allowed organisms to thrive in transitional environments between land and sea provided the foundation for later evolutionary radiations when environmental conditions became more stable. The genetic legacy of these prehistoric adaptations can still be detected in some modern organisms. Certain plant families retain physiological mechanisms for dealing with saltwater exposure and extreme humidity that appear to be evolutionary holdovers from prehistoric greenhouse periods. These genetic signatures provide insights into the adaptive strategies that allowed life to persist through extreme environmental transitions. Understanding these biological responses to prehistoric environmental extremes provides crucial context for predicting how modern ecosystems might adapt to rapid environmental change. The evolutionary innovations that emerged during prehistoric greenhouse periods demonstrate that life can adapt to environmental conditions far more extreme than current experience. But they also reveal that such adaptations require timescales that may not be available under current rates of environmental change. The speed of current environmental change represents perhaps the greatest challenge for biological adaptation. Prehistoric organisms had millions of years to develop the physiological and behavioral adaptations needed to thrive under extreme greenhouse conditions. Modern organisms face environmental changes that could reach prehistoric extremes within centuries rather than millennia. This compression of evolutionary timescales means that adaptation strategies that worked during prehistoric transitions may not be viable under current conditions. Instead of gradual evolutionary adaptation, modern biological communities may need to rely on ecological flexibility, migration, and human-assisted adaptation to survive rapid environmental transitions. Conservation strategies for managing these potential transitions require fundamentally different approaches than current conservation methods. Instead of focusing on preserving existing ecosystems in their current locations, conservation efforts may need to anticipate ecosystem migrations and assist biological communities in adapting to new environmental conditions. The prehistoric record provides valuable insights into which types of organisms and ecosystems are most likely to survive rapid environmental transitions. Generalist species that can tolerate wide ranges of environmental conditions tend to fare better than specialists adapted to narrow environmental niches. Organisms with high dispersal capabilities and rapid reproduction rates can adapt more quickly to changing conditions than those with long generation times and limited mobility. Ecosystem diversity and complexity also play important roles in determining resilience to environmental change. The prehistoric record shows that simple ecosystems dominated by a few highly productive species can sometimes persist through extreme environmental conditions better than complex ecosystems with many interdependent species. However, these simple ecosystems often lack the stability and resilience of more complex biological communities. While they may survive initial environmental transitions, they can be vulnerable to further environmental changes or biological invasions that more complex ecosystems might resist. The implications for modern conservation strategies are complex and sometimes counterintuitive. Protecting ecosystem complexity and biodiversity remains important for long-term ecological stability, but preparing for rapid environmental transitions may also require identifying and supporting the most resilient components of biological communities. Assisted migration of species and ecosystems represents one potential strategy for managing biological responses to rapid environmental change. The prehistoric record shows that organism and ecosystem migrations were crucial for surviving major environmental transitions. However, prehistoric migrations occurred over millions of years and across landscapes that were not fragmented by human development. Modern assisted migration efforts face challenges that have no prehistoric precedent. Moving species and ecosystems across landscapes dominated by human infrastructure requires careful planning and coordination between conservation efforts, land management, and human communities. The development of climate-adapted crop varieties provides another example of how prehistoric biological adaptations might inform modern strategies. Many crop plants have lost genetic diversity through centuries of selective breeding for specific environmental conditions. Reintroducing genetic diversity from wild relatives or developing new varieties based on prehistoric plant adaptations could enhance agricultural resilience under changing environmental conditions. Biotechnology offers additional possibilities for incorporating prehistoric biological adaptations into modern organisms. Understanding the genetic and physiological mechanisms that allowed prehistoric organisms to thrive under extreme environmental conditions could inform the development of crops, livestock, and other organisms adapted to future environmental scenarios. However, these technological approaches to biological adaptation raise complex ethical and ecological questions about human intervention in evolutionary processes. The prehistoric record shows that biological adaptation to extreme environmental conditions often involved fundamental changes in organism physiology and behavior that took millions of years to develop and integrate into stable ecosystem relationships. Rapid technological interventions to enhance organism adaptation could have unintended consequences that are difficult to predict or control. The complexity of prehistoric biological adaptations suggests that successful adaptation to extreme environmental conditions requires not just individual organism modifications, but entire ecosystem reorganizations. The social implications of managing biological responses to prehistoric scale environmental change extend far beyond conservation biology. Human societies depend on biological systems for food production, water purification, climate regulation, and many other essential services. Disruptions to these biological systems could affect human societies as profoundly as direct environmental changes. Agricultural systems represent the most immediate concern. Modern agriculture depends on relatively stable environmental conditions and biological communities that have been developed over thousands of years of human selection and management. Rapid environmental transitions could disrupt these agricultural systems faster than new ones can be developed and deployed. The prehistoric record provides some insights into biological productivity under extreme environmental conditions. But translating these insights into practical agricultural strategies presents significant challenges. Prehistoric biological communities were adapted to environmental conditions over millions of years and operated in ecosystems very different from modern agricultural landscapes. Developing agricultural systems that can function under prehistoric environmental conditions would likely require fundamental changes in crop selection, farming practices, and food distribution systems. The scale of these changes could affect food security for billions of people and require unprecedented coordination between agricultural research, land management, and social policy. Water resources present another critical interface between biological and human systems. Prehistoric wetland ecosystems played crucial roles in water purification and flood control, but these systems operated under environmental conditions very different from current water management needs. Modern water infrastructure is designed to operate under current climatic and hydrological conditions. Changes in precipitation patterns, river flow, and coastal dynamics associated with prehistoric scale environmental change could overwhelm current water management systems. Understanding how prehistoric biological systems managed water resources could inform the development of more resilient water management strategies. However, prehistoric biological water management operated over vast spatial scales and long time periods that may not be compatible with modern human settlement patterns and infrastructure. The health implications of biological responses to prehistoric environmental conditions also require consideration. Many modern disease patterns are influenced by environmental conditions that affect both human health directly and the biological communities that harbour disease organisms. Changes in temperature, humidity, and precipitation patterns could alter the distribution of disease vectors, the survival of pathogens, and the effectiveness of human immune responses. The prehistoric record provides limited insights into these health implications because human populations during previous greenhouse periods were very different from modern human societies. The mental health implications of living through biological and environmental transitions of prehistoric magnitude also deserve consideration. Human psychological and cultural development occurred under relatively stable environmental conditions. Rapid changes in biological communities and environmental conditions could create psychological stresses that exceed current understanding and treatment capabilities. Educational systems face the challenge of preparing people to understand and respond to biological and environmental changes that exceed current experience. Traditional ecological knowledge and biological education are based on organisms and ecosystems that developed under current environmental conditions. Preparing for prehistoric-scale environmental change requires developing new forms of biological and ecological literacy that can help people understand and adapt to biological communities and environmental conditions outside the range of current experience. The international cooperation required for managing biological responses to prehistoric-scale environmental change exceeds current institutional capabilities. Biological communities and ecosystem services cross national boundaries and operate on spatial and temporal scales that require unprecedented levels of international coordination. Research priorities for understanding biological responses to prehistoric environmental conditions increasingly focus on integrating paleobiological evidence with modern ecological research. Understanding how biological systems functioned under prehistoric environmental conditions requires combining geological evidence with laboratory experiments and field studies of modern organisms under controlled conditions. The urgency of this research stems from the rapid pace of current environmental change and the long timescales required for biological adaptation. Decisions made about conservation strategies, agricultural development, and ecosystem management over the next few decades could determine how successfully biological systems adapt to environmental changes that may persist for thousands of years. The prehistoric record ultimately reveals that biological systems can adapt to environmental conditions far more extreme than current experience, but that such adaptations require either very long timescales for evolutionary change or very specific ecological conditions that may not be available under current patterns of human development. Understanding these biological dimensions of prehistoric environmental extremes provides crucial context for evaluating potential future scenarios and developing strategies for managing the intersection between human societies and biological systems under conditions that exceed all historical precedent. The story of prehistoric sea levels and the biological communities that thrived under those conditions challenges us to think beyond current assumptions about the relationships between environment and life. These ancient biological adaptations remind us that life on Earth has persisted through environmental changes far more extreme than current projections. But they also reveal that such persistence often required fundamental reorganizations of biological communities and ecosystem relationships that took millions of years to develop and stabilize. As we face the possibility of environmental changes that could approach prehistoric extremes within human timescales, understanding these ancient biological responses becomes not just academically interesting, but essential for making informed decisions about how to prepare human societies and biological systems for futures that may bear little resemblance to the world that shaped our current understanding of life on Earth. The relationship between prehistoric sea levels and modern understanding becomes even more compelling when we examine how these ancient conditions might inform our response to current environmental challenges. The mechanisms that drove sea levels to extraordinary heights millions of years ago haven't simply vanished from Earth's playbook. They're dormant, waiting in the wings like actors between scenes, ready to return when atmospheric and geological conditions align once more. What makes this particularly sobering is the trajectory we're currently following. Atmospheric carbon dioxide levels have climbed steadily from pre-industrial concentrations of 280 parts per million to over 420 parts per million today. While this might seem modest compared to the 1,000+ parts per million that characterize prehistoric greenhouse periods, we're moving in that direction at unprecedented speed. The geological record shows us that atmospheric carbon dioxide concentrations of 600 to 800 parts per million were sufficient to trigger significant ice sheet melting and substantial sea level rise during the Pliocene period just 3 million years ago. At current emission rates, we could reach those concentrations within decades rather than millennia. This compression of timescales creates a situation that has no direct prehistoric precedent. During the Pliocene, when atmospheric conditions were similar to current projections for the late 21st century, sea levels stood 22 meters higher than today. This elevation required the near-complete loss of the Greenland ice sheet, significant portions of the West Antarctic ice sheet, and vulnerable areas of the East Antarctic ice sheet. The marine isotope records from this period reveal that these ice sheet reductions occurred even under relatively modest warming compared to prehistoric greenhouse extremes. But the Pliocene example represents just the beginning of what becomes possible as atmospheric greenhouse gas concentrations continue to rise. The relationship between atmospheric carbon dioxide and global temperature isn't linear. Climate sensitivity increases as concentrations climb higher, meaning that each additional increment of greenhouse gas produces larger temperature responses than the previous increment. This enhanced climate sensitivity occurs because multiple feedback loops begin operating simultaneously as temperatures rise. Ice albedo feedback accelerates as reflective ice surfaces disappear and are replaced by dark ocean or land surfaces that absorb more solar energy. Water vapor feedback intensifies as warmer air holds more moisture, amplifying greenhouse effects. Permafrost feedback releases stored carbon as frozen soils thaw, adding to atmospheric greenhouse gas concentrations. These feedback mechanisms operated during prehistoric greenhouse periods, but they developed over millions of years as atmospheric conditions gradually shifted. Modern rapid emissions could trigger multiple feedback loops simultaneously, creating responses that overshoot even prehistoric temperature extremes before stabilizing mechanisms have time to engage. The thermal expansion component of sea level rise provides a particularly clear example of how modern rapid warming could produce effects that exceed prehistoric analogues. During the Eocene greenhouse period, ocean temperatures rose gradually over millions of years, allowing thermal expansion to reach equilibrium with atmospheric conditions. Deep ocean temperatures eventually reached 13 degrees Celsius compared to less than 2 degrees today. But this thermal expansion occurred slowly as heat gradually penetrated throughout the entire ocean volume. Modern rapid warming is heating surface waters much faster than deep waters, creating temperature gradients that didn't exist during prehistoric greenhouse periods. As this surface heat eventually penetrates to greater depths over coming centuries, thermal expansion effects could continue accelerating long after atmospheric greenhouse gas concentrations stabilize. Recent oceanographic studies have revealed that the deep ocean contains enormous reserves of cold water that represent potential for continued thermal expansion even under stable atmospheric conditions. If deep ocean temperatures eventually equilibrate with surface warming, thermal expansion could contribute several meters to sea level rise beyond what current models predict based on surface temperature changes alone. The ice sheet dynamics that contributed to prehistoric sea level extremes also operate on timescales that create complex interactions with modern rapid warming. Ice sheets respond to temperature changes through multiple mechanisms that operate at different speeds. Surface melting can increase within years or decades, while ice sheet flow dynamics and bedrock adjustment operate over centuries to millennia. During prehistoric warm periods, ice sheets had millions of years to reach equilibrium with atmospheric conditions. Complete ice sheet loss occurred gradually as ice margins retreated and ice thickness decreased over vast time scales. Modern rapid warming could trigger ice sheet responses that are initially more dramatic than prehistoric analogues because ice sheets haven't had time to adjust gradually to changing conditions. The West Antarctic ice sheet provides a particularly concerning example of how modern ice sheet dynamics might differ from prehistoric patterns. This ice sheet sits on bedrock that lies below sea level, making it vulnerable to marine ice sheet instability once warming ocean waters penetrate beneath the ice. Prehistoric warm periods eventually eliminated this ice sheet, but the process likely occurred over hundreds of thousands of years. Recent glaciological observations suggest that marine ice sheet instability could cause much more rapid ice sheet collapse under modern warming rates. Once initiated, this process could be difficult to reverse even if atmospheric warming were halted. The potential for rapid West Antarctic ice sheet collapse represents a sea level rise contribution of 3 to 4 meters that could occur over centuries rather than millennia. The Greenland ice sheet presents different but equally significant vulnerabilities under rapid modern warming. This ice sheet experiences enhanced surface melting during warm summers, creating feedback loops that accelerate ice loss. Dark areas of exposed ice and meltwater absorb more solar energy than white snow, creating additional melting that expands these dark areas further. Recent satellite observations have documented accelerating mass loss from the Greenland ice sheet, with annual ice loss rates that have increased dramatically over the past few decades. While complete Greenland ice sheet loss would require sustained warming over many centuries, the acceleration of ice loss processes suggests that significant contributions to sea level rise could occur much sooner. The interaction between ice sheet dynamics and oceanic thermal expansion creates complex patterns of regional sea level change that differ significantly from uniform global sea level rise. As ice sheets lose mass, their gravitational influence on surrounding ocean waters decreases, causing sea level to drop near the ice sheets, but rise more dramatically in distant regions. This gravitational effect means that ice sheet melting in Greenland and Antarctica causes particularly large sea level rise along coastlines thousands of kilometers away. Coastal areas along the eastern United States and southeastern Asia experience enhanced sea level rise from Greenland ice sheet melting, while regions distant from Antarctica see amplified effects from Antarctic ice sheet loss. These regional variations in sea level response mean that some coastal areas could experience sea level rise that significantly exceeds global average projections. Understanding these regional patterns becomes crucial for coastal planning and adaptation strategies, particularly for major population centers located in regions of enhanced sea level response. The oceanic circulation changes that occurred during prehistoric greenhouse periods also provide insights into potential future ocean behavior under continued warming. During extreme greenhouse periods, the temperature differences between equatorial and polar regions became much smaller than today, reducing the driving forces for oceanic circulation. This weakening of oceanic circulation had profound effects on heat distribution, nutrient cycling, and biological productivity throughout the ocean system. Reduced circulation meant that heat accumulated more efficiently in ocean waters, enhancing thermal expansion effects. It also led to the development of oxygen minimum zones and anoxic conditions in many ocean regions. Modern observations already show evidence of circulation changes in response to current warming trends. The Atlantic meridional overturning circulation, which transports warm surface waters northward and cold deep waters southward, has shown signs of weakening over recent decades. While this circulation system is still far from the stagnant conditions of prehistoric greenhouse periods, continued weakening could accelerate both regional and global sea level rise. The breakdown of modern oceanic circulation would have cascading effects throughout the climate system. Reduced heat transport to polar regions could paradoxically accelerate ice sheet melting by concentrating warm waters in regions where they can access ice sheet margins. Reduced deep water formation could enhance ocean stratification and reduce the ocean's capacity to absorb atmospheric carbon dioxide. These circulation changes also affect the distribution of marine productivity and the cycling of nutrients throughout ocean systems. During prehistoric greenhouse periods, altered circulation patterns led to massive changes in marine ecosystems and biogeochemical cycling. Similar changes under modern rapid warming could affect ocean ecosystems in ways that cascade throughout global food webs. The chemical composition of seawater during prehistoric greenhouse periods also differed substantially from modern oceanic chemistry. Enhanced volcanic activity and altered biological productivity created ocean chemistry conditions that influenced both thermal expansion and ice sheet stability. While modern oceans aren't experiencing the massive volcanic inputs that characterized prehistoric greenhouse periods, other chemical changes could produce similar effects. Ocean acidification from increasing atmospheric carbon dioxide concentrations represents one of the most significant chemical changes affecting modern oceans. As seawater becomes more acidic, it affects the ability of marine organisms to build calcium carbonate shells and skeletons. This could reduce the biological carbon pump that helps regulate atmospheric carbon dioxide concentrations. The interaction between ocean acidification and thermal expansion creates complex feedback loops that could amplify sea level rise beyond what temperature effects alone would produce. Reduced biological carbon sequestration could enhance atmospheric greenhouse gas concentrations, accelerating warming and thermal expansion. Changes in marine ecosystem productivity could also affect ocean circulation patterns and heat distribution. The timescales over which these chemical and biological changes operate create additional complexities for predicting future sea level behavior. While thermal expansion responds relatively quickly to temperature changes, chemical and biological adjustments in ocean systems occur over decades to centuries. This means that ocean chemistry effects on sea level rise might continue accelerating long after atmospheric conditions stabilize. Understanding these complex interactions between atmospheric composition, ocean chemistry, ice sheet dynamics, and thermal expansion becomes crucial for developing accurate projections of future sea level rise. The prehistoric record provides essential data for testing and improving models of these interactions, but significant uncertainties remain about how these processes behave under rapid modern warming rates. The paleoclimate modeling community has made substantial progress in reproducing prehistoric greenhouse conditions, but significant challenges remain in accurately simulating the extreme temperatures, circulation patterns, and chemical conditions that characterized ancient high sea level periods. These modeling challenges partly reflect the computational demands of simulating such extreme climate states, but they also highlight gaps in understanding of the physical processes involved. Recent advances in paleoclimate reconstruction have provided increasingly detailed data about prehistoric climate conditions, offering new opportunities to test and improve climate models. High-resolution marine sediment records, ice core data from ancient ice sheets, and terrestrial paleoclimate archives provide detailed information about temperature, precipitation, and atmospheric composition during prehistoric greenhouse periods. These paleoclimate data reveal that prehistoric climate systems exhibited variability and instability that exceeds anything observed in the modern instrumental record. Rapid climate transitions, extreme weather events, and non-linear responses to atmospheric forcing were common features of prehistoric greenhouse periods. This variability suggests that modern climate systems under greenhouse forcing might exhibit similar instability. The implications of this prehistoric climate variability extend beyond academic interest. Understanding the range of natural climate variability under greenhouse conditions provides crucial context for interpreting current climate observations and projecting future climate behavior. The prehistoric record suggests that greenhouse climate systems can exhibit rapid transitions and extreme events that exceed current climate model predictions. This prehistoric climate variability also affects projections of sea level rise by influencing the rates and patterns of ice sheet melting, thermal expansion, and oceanic circulation changes. If future climate systems exhibit the variability characteristic of prehistoric greenhouse periods, sea level rise could occur in rapid pulses rather than gradual trends. The geological evidence for rapid sea level changes during prehistoric greenhouse periods provides sobering insights into potential future scenarios. Meltwater pulse events preserved in marine sediment cores show that sea levels could rise by several meters within centuries during periods of ice sheet instability. These rapid sea level changes occurred even during generally stable greenhouse climate conditions. The triggers for these rapid sea level changes weren't always obvious from the geological record. Some meltwater pulses appeared to occur during periods of relatively stable atmospheric conditions, suggesting that internal dynamics of ice sheets or ocean systems could trigger rapid changes even without external forcing. This potential for rapid sea level changes under seemingly stable conditions has important implications for coastal planning and adaptation strategies. Even if atmospheric greenhouse gas concentrations were stabilized at current levels, the potential for continued ice sheet adjustment and thermal expansion could produce sea level rise that continues for centuries to millennia. The economic implications of prehistoric scale sea level rise scenarios extend far beyond current estimates of climate change costs. Most economic analyses of sea level rise focus on relatively modest scenarios of 1 to 2 meters of rise over the coming century. But prehistoric sea levels suggest that much larger changes are possible under continued greenhouse gas emissions. Sea level rise of 10 to 20 meters would inundate coastal areas that currently support billions of people and trillions of dollars in infrastructure and economic activity. The costs of protecting or relocating this infrastructure would likely exceed the total economic output of many nations. More fundamentally, such large sea level changes would require complete reorganization of global trade networks, agricultural systems, and population distributions. The timeframes over which these changes might occur create additional economic challenges. While prehistoric sea level rise occurred over millions of years, modern rapid warming could compress these changes into centuries to millennia. This acceleration means that adaptation strategies must be developed and implemented much faster than prehistoric biological and geological systems required for adjustment. Current economic institutions and planning frameworks are poorly equipped to handle adaptation requirements that extend over such long timeframes. Most economic planning operates over decades rather than centuries, and most infrastructure is designed with operational lifespans of 50 to 100 years. Preparing for sea level changes that could persist for thousands of years requires developing new approaches to long-term economic planning and infrastructure design. The social implications of prehistoric scale sea level rise present equally daunting challenges. Human societies have never experienced environmental changes comparable to the transitions documented in the prehistoric record. The psychological, cultural, and political effects of such dramatic environmental changes are difficult to predict, but could be profound. Mass migrations triggered by sea level rise of prehistoric magnitude would involve population movements that dwarf anything in human history. Current refugee and migration systems are already strained by relatively modest population movements. Managing migrations involving hundreds of millions or billions of people would require unprecedented international cooperation and institutional innovation. The breakdown of existing political boundaries and economic relationships under prehistoric scale environmental change could trigger social upheaval that exceeds current institutional capacities to manage. Historical examples of social responses to environmental change provide limited guidance because none approach the scale and speed of potential future transitions. Cultural implications represent another dimension of prehistoric scale environmental change that receives little attention in current climate discussions. Many human cultures have developed deep connections to specific landscapes and environmental conditions. The loss of these landscapes to rising seas would represent cultural disruptions that extend far beyond practical adaptation challenges. Religious and spiritual traditions often incorporate specific geographic features and environmental relationships that could be fundamentally altered by prehistoric scale sea level rise. Adapting these cultural and spiritual traditions to dramatically different environmental conditions presents challenges that go beyond technological or economic adaptation strategies. Educational systems face the challenge of preparing people to understand and respond to environmental changes that exceed current experience and historical precedent. Traditional geographic, historical, and scientific education is based on environmental conditions that may not persist under continued greenhouse gas emissions. Developing educational approaches that help people understand and prepare for prehistoric scale environmental change requires incorporating paleoclimate science, long-term thinking, and systems perspectives that aren't well represented in current educational curricula. This educational challenge becomes particularly important for children and young people who may live through environmental transitions that exceed anything in recorded history. The technological implications of prehistoric scale sea level rise also present significant challenges for current industrial and technological systems. Most modern technology is designed to operate under current environmental conditions and may not function effectively under the extreme temperatures, humidity, and chemical conditions that characterized prehistoric greenhouse periods. Infrastructure systems represent particularly vulnerable components of technological civilization under prehistoric environmental scenarios. Transportation networks, communication systems, and industrial facilities are designed based on assumptions about environmental stability that may not hold under continued greenhouse forcing. Developing technologies that can function under prehistoric environmental conditions requires anticipating environmental changes that exceed current engineering experience. This technological adaptation challenge becomes particularly important for systems that are essential for human survival and social organization. The international cooperation required for managing prehistoric scale environmental change exceeds current institutional capacities. Environmental changes on the scale documented in the prehistoric record affect all regions simultaneously and require coordinated responses that cross national boundaries and time horizons. Current international institutions are designed to address challenges that operate over political timeframes of years to decades. Managing environmental changes that persist for centuries to millennia requires developing new forms of international cooperation that can maintain coordination across multiple generations and changing political circumstances. The scientific research priorities for understanding prehistoric environmental change increasingly focus on improving projections of future climate behavior under extreme greenhouse gas scenarios. While significant progress has been made in understanding prehistoric climate systems, major uncertainties remain about how these systems might respond to rapid modern warming rates. Interdisciplinary collaboration between paleoclimate researchers, climate modelers, and social scientists becomes essential for developing comprehensive understanding of potential future scenarios. The complexity of prehistoric environmental systems requires integrating evidence from geology, biology, chemistry, physics, and social sciences. The urgency of this research stems from the rapid pace of current environmental change and the long timeframes over which climate system responses operate. Decisions made about greenhouse gas emissions over the next few decades could determine environmental conditions for thousands of years. Understanding potential long-term consequences becomes essential for making informed decisions about current policies and actions. International scientific coordination also becomes crucial for advancing this research effectively. The global nature of prehistoric environmental change means that evidence is preserved in geological formations around the world. Coordinating research efforts across different regions, institutions, and disciplines is necessary for developing comprehensive understanding of these ancient climate systems. The prehistoric record ultimately serves as both a warning and a guide for navigating potential future environmental change. It warns us that Earth's climate system can undergo transitions far more dramatic than anything in human experience. But it also provides crucial information about how these transitions occur, what factors control their development, and how biological and geological systems respond to extreme environmental change. The extreme sea levels documented in Earth's prehistoric past remind us that our planet has operated under conditions far different from those that shaped human civilization. These ancient oceanic extremes challenge us to think beyond comfortable assumptions about environmental stability and to prepare for futures that may bear little resemblance to the world we know today. Understanding prehistoric sea levels doesn't provide simple answers about future environmental change, but it does reveal the true range of possibilities that Earth's climate system can produce. The mechanisms that drove prehistoric sea levels to heights of 250 meters above present levels haven't disappeared from Earth's repertoire. They remain as potential responses to atmospheric conditions that human activities are rapidly approaching. The choice we face isn't whether Earth's climate system will respond to continued greenhouse gas emissions. The prehistoric record makes clear that it will. The choice is whether we prepare for the magnitude of response that the geological record suggests is possible, or whether we continue planning based on the assumption that future environmental change will remain within the narrow range of recent human experience. The extreme sea levels of Earth's prehistoric past offer us a glimpse into our planet's climate potential when operating under full greenhouse conditions. These ancient oceanic giants stand as monuments to Earth's capacity for environmental transformation, carved in stone across continents, and preserved in the chemistry of ancient marine sediments. They remind us that the familiar world of stable coastlines and predictable seasons represents just one possible configuration of our planet's environmental systems. As we stand at the threshold of potentially triggering our own transition toward prehistoric atmospheric conditions, these ancient sea level extremes serve as both a warning and a roadmap. They show us what becomes possible when Earth's climate machinery shifts into high gear, driven by atmospheric greenhouse gas concentrations that we're rapidly approaching through our own emissions. The story of prehistoric sea levels isn't just about ancient oceans that no longer exist. It's about understanding the full range of our planet's environmental potential and recognizing that the choices we make today about greenhouse gas emissions could determine whether future generations inherit a world that resembles the stable conditions that nurtured human civilization, or whether they face the challenge of adapting to oceanic extremes that dwarf anything in human experience. These prehistoric oceanic giants remind us that Earth's climate system operates on scales of power and transformation that humble human assumptions about environmental control. But they also demonstrate our planet's remarkable capacity for supporting life under conditions far more extreme than current experience suggests is possible. The question that remains is whether human societies can develop the wisdom, cooperation, and technological capability needed to navigate potential transitions toward environmental conditions that have no precedent in human history. The prehistoric record offers no guarantees about how such transitions might unfold or what challenges they might present, but it does provide essential insights into the physical processes, biological responses, and environmental relationships that operate when Earth's climate system shifts into configurations that sustained oceanic giants reaching heights that could submerge modern cities beneath hundreds of meters of warm, ancient seas. In the end, the extreme sea levels of Earth's prehistoric past serve as a profound reminder that our planet's environmental systems possess a capacity for change that exceeds human imagination. These ancient oceanic extremes challenge us to expand our understanding of what's possible on Earth, and to prepare for futures that may require adapting human civilization to environmental conditions that shaped our planet long before humans existed, and that could shape it again long after current concerns about modest sea level rise have been forgotten beneath waters that reach heights known only to Earth's most ancient and extraordinary oceanic past. The legacy of these prehistoric oceanic extremes extends far beyond their immediate geological impact. They fundamentally reshaped the evolutionary trajectory of life on Earth in ways that continue to influence modern ecosystems. During periods when sea levels reached their maximum heights, marine environments didn't just expand geographically. They created entirely new evolutionary laboratories where organisms developed adaptations that would persist long after the waters receded. Consider the evolutionary innovations that emerged during these periods of maximum marine expansion. The extensive shallow seas of the Cretaceous became breeding grounds for evolutionary experimentation on scales that modern oceans simply cannot support. With vast continental shelves submerged under warm, nutrient-rich waters, marine organisms had access to ecological niches that don't exist in today's deeper, cooler oceans. The ammonites that flourished during these periods developed shell architectures and swimming capabilities that represent some of the most sophisticated engineering solutions in the history of life. These weren't just larger versions of modern nautiloids. They were creatures that had evolved complex internal shell structures, jet propulsion systems, and sensory capabilities specifically adapted to the unique conditions of prehistoric shallow seas. The belemnites that dominated Cretaceous oceans evolved internal shells that functioned as sophisticated ballast systems, allowing them to control their buoyancy with precision that enabled rapid vertical migrations through water columns that could extend for hundreds of meters across flooded continental platforms. Their fossilized remains preserve evidence of swimming capabilities and predatory behaviors that were specifically adapted to hunting in the vast open waters of inland seas. But these marine innovations extended far beyond individual species adaptations. Entire ecosystem architectures developed during periods of maximum sea level that created biological relationships and energy flows unlike anything in modern marine environments. The rudest bivalves that built massive reef systems during the Cretaceous created three-dimensional habitat structures that supported biological communities of extraordinary diversity and productivity. These rudest reefs weren't simply ancient versions of modern coral reefs. They were biological constructions that created habitat complexity and ecological relationships specifically adapted to the warm, chemistry-rich waters of prehistoric shallow seas. The fossilized remains of these reef systems preserve evidence of biological productivity and ecosystem integration that exceeded anything observed in modern marine environments. The microscopic organisms that formed the base of these prehistoric marine food webs also developed innovations that fundamentally altered global biogeochemical cycling. The coccolithophores that created massive chalk deposits weren't just producing calcium carbonate shells for protection. They were engineering sophisticated cellular mechanisms that could function efficiently under the extreme temperature and chemistry conditions of greenhouse ocean environments. These microscopic marine organisms developed photosynthetic pathways, cellular regulation systems, and reproductive strategies that allowed them to maintain massive population densities under environmental conditions that would be instantly lethal to their modern relatives. The scale of their biological productivity literally changed the chemistry of Earth's oceans and atmosphere over millions of years. The planktonic foraminifera that lived in these prehistoric oceans evolved shell architectures and cellular organizations that reveal sophisticated adaptations to extreme temperature gradients, altered ocean chemistry, and enhanced atmospheric carbon dioxide concentrations. Their fossilized remains provide detailed records of how single-celled organisms can engineer cellular solutions to environmental challenges that exceed anything in modern marine environments. These evolutionary innovations weren't limited to marine environments. The extensive coastal wetlands and transitional ecosystems created by extreme sea levels became evolutionary laboratories for organisms transitioning between aquatic and terrestrial lifestyles. Early flowering plants developed physiological mechanisms for dealing with saltwater intrusion, periodic flooding, and atmospheric conditions that differed dramatically from modern terrestrial environments. The early mammals that lived in these dynamic coastal environments evolved behavioral and physiological adaptations that allowed them to exploit resources from both marine and terrestrial ecosystems. These weren't simply opportunistic feeding strategies. They represented fundamental evolutionary innovations in metabolism, sensory systems, and reproductive strategies that allowed mammals to thrive in environments that shifted regularly between aquatic and terrestrial conditions. The reptilian communities that dominated these transitional environments developed thermoregulatory mechanisms, locomotory adaptations, and reproductive strategies that were specifically suited to the extreme humidity, temperature fluctuations, and periodic flooding characteristic of extensive coastal wetland systems. Many of these adaptations provided the evolutionary foundation for later radiations when environmental conditions became more stable. But perhaps the most remarkable aspect of these evolutionary innovations was their persistence through subsequent environmental transitions. Many of the physiological mechanisms, behavioral strategies, and ecological relationships that evolved during periods of extreme sea levels continue to influence evolutionary trajectories long after ocean levels returned to more moderate heights. The genetic signatures of these prehistoric adaptations can still be detected in modern organisms, providing insights into evolutionary responses to environmental extremes that have no modern analogues. Certain plant families retain cellular mechanisms for salt tolerance and flood adaptation that appear to be evolutionary holdovers from prehistoric greenhouse periods when extensive coastal flooding was the norm rather than the exception. Some marine organisms carry genetic signatures that suggest their ancestors developed specialized physiological mechanisms for dealing with the extreme temperatures and altered chemistry conditions of prehistoric greenhouse oceans. These genetic legacies provide clues about adaptive strategies that allowed life to persist through environmental transitions far more dramatic than anything in recent Earth history. The evolutionary responses to prehistoric sea level extremes also reveal important principles about biological adaptation that extend beyond specific environmental conditions. The organisms that successfully navigated these extreme environmental transitions typically exhibited high levels of phenotypic plasticity, allowing them to adjust their physiology and behavior in response to changing conditions without requiring genetic changes. This phenotypic plasticity appears to have been crucial for surviving the rapid environmental fluctuations that characterize transitions between different sea level regimes. Even during periods when average sea levels were extremely high, geological evidence suggests that significant fluctuations occurred on shorter timescales, requiring organisms to be capable of adjusting to environmental changes that happened faster than evolutionary adaptation could occur. The social structures and behavioral patterns that evolved during periods of extreme sea level also provided insights into how complex biological communities can maintain stability under highly variable environmental conditions. Many of the marine reptiles that dominated prehistoric oceans appear to have developed sophisticated social behaviors and migration patterns that allowed them to track optimal environmental conditions across vast geographic areas. These behavioral adaptations were particularly important during periods when oceanic circulation patterns were fundamentally different from modern conditions. The ability to navigate across vast inland seas and locate optimal feeding and breeding areas required sensory capabilities and navigation systems that were specifically adapted to the unique geographic and environmental conditions of prehistoric high sea level periods. The reproductive strategies that evolved during these periods also reflect adaptations to environmental conditions that have no modern analogues. Many prehistoric marine organisms developed reproductive cycles that were synchronized with environmental fluctuations specific to greenhouse climate conditions, such as seasonal patterns driven by atmospheric circulation systems that no longer exist. These reproductive adaptations often involve complex life cycles that took advantage of the unique environmental opportunities provided by extensive shallow seas, coastal wetlands, and transitional ecosystems. The ability to exploit multiple habitat types during different life stages provided evolutionary advantages that were specifically suited to the dynamic environmental conditions of prehistoric high sea level periods. The geological record doesn't lie. For hundreds of millions of years, Earth operated as a fundamentally different planet, where oceans towered hundreds of meters above anything we know today. These weren't brief anomalies or temporary floods. They were stable climate states that persisted longer than entire evolutionary lineages, reshaping continents and rewriting the rules of how our planet's environmental systems function. What makes this story particularly urgent is that we're rapidly recreating the atmospheric conditions that sustained these ancient oceanic giants. The volcanic forces that once drove sea levels to extraordinary heights may be dormant, but the greenhouse gas concentrations that amplified their effects are climbing toward prehistoric levels through our own emissions. The mechanisms that created these ancient waterworlds haven't disappeared. They're simply waiting for the right atmospheric trigger to awaken once more. Understanding these prehistoric extremes reveals the true range of Earth's climate sensitivity and challenges every assumption we hold about environmental stability. The familiar coastlines, predictable seasons, and moderate sea levels of recent history represent just one possible configuration of our planet's environmental machinery. The ancient record shows us what becomes possible when Earth's climate system shifts into configurations that operated by completely different rules. These prehistoric oceanic extremes serve as both a warning and a roadmap, revealing the physical processes that could reshape our world and the biological responses that allowed life to persist through environmental changes that dwarf anything in human experience. They remind us that the choices we make today about atmospheric composition could determine whether future generations inherit a world resembling the stable conditions that nurtured human civilization, or whether they face the challenge of adapting to oceanic extremes that could transform geography itself.